datasets from SAS help. SAS help is a library where you have a lot of test datasets. So we will run this code first, this data statement, wherein we are importing the data from the SAS help to the work library. Yes, now we can see the dataset cards is there in the work library. So the import is successful. Okay. When we have the data, the very first thing that we should be doing is that to open the datasets. To do that, you double click on the dataset and you will see what all variables are there and what how the dataset look like. So the dataset is having variables related to the cars. You have make of the car, model of the car, type, origin, and then many other variables like horsepower, engine size, weight, length. So how many observations are there? If you drag it below, you will see that total 420 observations are there. Okay, and how many variables are there? So in the top of the data set, you have the first row has the variables, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in total you have 15 variables and 428 observations. We can do it better. You don't have to go to the data set and count the variables and then take a note of what are the variables are. We can use Proc contents and we can do it very easily. So let's run Proc content on that. So the syntax is like this: Proc contents data, and then you give the name of the data set. The output window, and you can see now you have the details about the dataset. So our dataset name is walk.cars. So walk is the library and cars is the name of the dataset. Okay. So when is it created? You have the date. You have the operating system where it is created. You have the number of observations. So you don't have to scroll it down and see what is the number of observations. Proc contents gives you the details. You have 428 observations. How many variables are there? 15 variables. We counted 15, right? So the system counts it for you, so you don't have to do it by yourself. Whether the data is compressed or sorted, no, it says that it's not sorted. And then you have the path where this data is stored. Down below you can see the number of variables, the variable names, as well as their the format, the type, and the label. So you have the variable names here, and then type of the variable, whether it's a numerical variable or it's a character variable or it's a date variable. So NUM stands for numerical variable, CHAR stands for character variable. So what is the difference? Numerical variables has numbers like length, weight, that kind of variable, whereas character variable will have variables like make of the car, non-quantitative variables which cannot be quantified, like model, make, the type of the car, or the origin of the car. These are the variables. And then you have variable length here. Okay, so you can change the length later on. And then you have the format. If it is blank, then the default format is there. Then there is variable label. Not all the variables has got labels. You can always have labels later on. So in the dataset there are few variables where you have the label. So what is the label? So label is an alternative name of the variable. Okay, so if a variable has a label, so when you see the data set, your actual variable name will not be shown there, your label name only be shown there. Why is it done? Say let's see, for example, you have engine size, right? So engine and size, they are just one word. Okay, there is no space between engine and size. If you have a space between them, it will not be considered as a variable name. Okay, so you cannot have a name of the variable having a space, blank space inside two words. That's not allowed in SAS. But how do we interpret? How do a non-statistician who doesn't know SAS, or who is a statistician but is not using SAS, how will he get to know what this variable means? Well, for that we use a different name, an alternative name, easier to understand, and that's the reason why we have like engine, then we have put a space there, and then size. So it's easily understandable, right? Similarly, you can see MTGCT. Okay, so what does that mean? Probably we don't know. So we have a detail or a better name for that, and we have given that. So that's the reason why we use label. Not necessarily we need to have labels for everything. It's an optional. If it is clearly understood, if the variable name is clearly understood, there is no reason why we should have a label there. Okay, so that's about proc content. So what is the use of proc content? If you want to see what all things are there in the dataset, you need to use proc content, and that's the first thing one need to do when somebody gets a dataset. Okay, so what if you want to save, or you want to have the details about the data in another dataset? Okay, so you just want to have the type and then the name of the variables, total number of observations, all that in a separate dataset. Okay, so for that, same syntax, you just have to use the out statement here. So you can see proc content data, then we have pencil car, which is the name of the dataset, and then out statement, and then you give a name to a name. So you can give any name. It will be saved in the work library. If you want to save in some permanent library, you just have to give some library name. Say for example, your permanent library is lib, so just put lib dot. So the cars underscore details will be saved in the lib library. Okay, but we don't have any library as such, so it will be saved in the default library, which is the work library. So let's run this. Yes, it's successful. So as we can see in the work library, car underscore details is saved. Let's open this. So we can see that you have the name of the library, then the variable names, variable types. So what does that 1 and 2 mean? So you need to check whether 1 is numeric or 2 is numeric. You can decode it also later on, and then total number of observations, date modify. So the details about the data set is now saved in another data set. Okay, you might need it in later point of time. What we need sometime is the number of variables and the name of the variables. Okay, so you just have to run this code and get your variable name saved in another data set, and it's very useful when you want to loop all your variables in a program, or you want to do something about it. So you will find it very useful there. Okay, so the next thing is that we'll do variable exploration with proc means. So what all things can we do using proc means? Okay, so the syntax is like this: proc means data, your data name, and then use the keyword var, and then put a variable name. For simplicity purpose, I have used only one variable name. Okay, you can use all the variables name at one time. At one go you can put all the variable names. Remember, in proc means you can use only the numeric variables. You can use character variables, but interpreting character variables in terms of its means, it's very difficult. So generally we use only the numeric variables in the proc means. So let's run this. So when we run this, we have the following. The proc means gives us, the first thing is your n, which is the count of observations, 428, Then the mean length. So what is a mean? Mean is nothing but your average, sum of the total or sum of all the observations by the number of observations. And then we have the standard deviation here, minimum value and the maximum value. So minimum value of length and the maximum value of length in the data set. Okay, so these values or these statistics are very important in many aspects. So before doing any statistical modeling, it's very important that we know what is the mean of the data, what is the standard deviation of the data, what is the minimum value, and what is the maximum value. So how is it going to help us? Say for example, the minimum value is 0. Okay, do you think that the length of a car can ever be 0? Well, it cannot be. So there must be some error in the data set, and we can just go and check it out. So sometimes the data might look very suspicious, and we need to go back and check whether the data is correct or not, and then we need to consult the company or the organization from where we have received our data set. Same thing about maximum value. If the maximum value is too high, say for example 500 meter, it's very unlikely you have a 500 unit. Very unlikely you will have that kind of a length of a car. So this really helps us knowing knowing the characteristics of the data set. So you might have heard about outliers. So what are the outliers? Outliers are the ones or the observations which are very different from the usual observation or the normal observations. Okay, they're very far apart. In statistical modeling, it is very difficult to model the data when you have outliers. So how do you know whether you have outliers in the data? One way of knowing whether you have outliers in the data set is to first see the mean, standard deviation, and minimum maximum. If you have a very high value in the maximum, probably that will be an outlier. A very minimum value, probably that observation can be taken as an outlier. Similarly, mean and standard deviation can also help. For example, if the mean is less and the standard deviation is quite high, that means there is a serious deviations from the mean value. Okay, that means some of the observations are at a very large distance from the mean. You expect that most of the observations will be located nearby the mean, not very far away from the mean. So high standard deviation is one way or one way in which you will get to know that there is possibility of having outlier, and you can confirm it by doing other type of exploratory data analysis, which we will study, and then you can take appropriate measure in dealing with this problem. So how do we deal with outliers? We will study that in another lecture. But this is the way you will get to know the characteristics of a numeric variable. So as I said in the beginning, you can do it for n number of variables. So you may have as many number of variables, and you can do the explorations. So I'm putting here length, weight, invoice, and energy size. Sorry, engine size, and then let me run this. You can see the same thing, your number of observation, mean, standard deviation, minimum, maximum. All these statistics are there for 4 variables. Okay. So what if you don't need all the statistics? You only need minimum, maximum, or a combination of this, or maybe 2 or 3 statistics at one time. Okay, I just want minimum and maximum, nothing else. So why do I do that? Okay, so proc means data, and then your data name, and then at the right of it just put maximum and minimum. Okay, and how do you know this? If it is blue, if it's a different color, it's not black, that means it's a keyword. So minimum maximum you just put there and just run, and in the output we'll have only minimum and maximum, nothing else. As you can see, for length we only have the minimum and maximum, nothing else. So that's important. For example, if I need only mean or standard deviation, so what I can do, so I'll write mean here and then standard deviation, and then I'll run it. So in the output I have only mean and standard deviation. And you can put as many variables as possible. Probably there is a limit, but you can go on to 30, 40, 50, any number of variables in the var statement. So there is another thing that we can do with proc means. We can also get to know the count of missing data, like how many observations are having missing values. Okay, we can count it. How do we do that? In the proc means we can use nmiss, and we can do that. So the syntax is like this: proc means data, and then the data name, and then write nmiss, nmiss. Okay, so I'm putting all the variables, all the 4 variables, and let's run this. In the output you can see the number of misses, or the number of the missing values. Well, in our data there is no missing value, so it 0 for all the variables. If you have a missing value, then it will give you how many observations in that particular value are missing. Okay, so to know the missing value even in character variables, you can use proc base, so that is not an issue. But for mean, standard deviation, having character variable won't make sense. So don't use mean, standard deviation for character variables, but you can always use character variables. Even I mean, if you want to know the count of the missing values. Now we will see that how do we do data exploration using proc frequency. So what is a frequency? Frequency is nothing but the count for each categories. So basically frequency is something that we are interested to know for a categorical variable. Okay, so for a categorical variable, of course standard deviation or mean won't make any sense, so we just need to see what is the count of each categories. Okay, so make is a categorical variable, so let's run. So the syntax is like this: proc freq, then data, and then you put your data name, table, and then your variable name. Okay, let's run this. See, so you have the different make and their corresponding frequencies. Okay, so you can count what is the highest number of frequency, what is the lowest number of frequency, and what is the corresponding percentage. You have the cumulative frequency at the right of it and the cumulative percentage at the extreme right. Okay, well, proc frequency helps us in many ways. Okay, so say for example the requirement is that we need to have a uniform frequency across all categories. We cannot afford to have just too many observation of one category and then too less observation of another category, or at least they should be similar, or there should not be a great deviation, or there is a great difference between the number of count or the number of frequency between two categories or different categories. And that's the requirement in many modeling exercises. So we'll get to know that by doing a proc frequency. So as you can see, you have the proc frequency for all the categories. and then based on this you can take the call, like whether you want to include some more observation, or you just want to leave out some of the categories which are either having very low frequency or very high frequency. Okay. Proc frequency can also be used for doing 2 by 2 cross tabulation, or 2 by 2 cross tabulation, even 3 by 3 cross tabulations. Okay, let's do the 2 by 2 cross tabulation first. So syntax remains same. So origin and type are the two variables where we want to do a 2 by 2 cross tabulations. Okay, so the syntax is like this: origin, then you put a cross mark, and then you put the another variable which is type. Let's run this. So as you can see, you have origin in the column, sorry, in the rows, and type in the column. So in Asia, how many hybrids are there? Only 3. In Asia, how many SUVs are there? 25. So in Europe, how many hybrid are there? 0. So that's the way in which you interpret a 2 by 2 cross tabulated matrix. So again, this also helps knowing the distribution of the data, how the data is distributed across different categories. And you can take two variables at the same time to get an idea about how is the distribution look like. For example, in Europe, how many sedans are there? 78. So that's quite huge. Similarly, in US, how many sedans are there? 90. Okay, so so somebody asks you like, what is the distribution of sedan across different origin? And then you can answer it very easily. So you have 94 in Asia, 78 in Europe, and 90 in US. So somebody may ask you, okay, give me an idea about how different type of vehicles are distributed across the in the US market. So you can say, in US we have no hybrid, we have 25 SUV, 90 sedan, 9 sports vehicle, 16 trucks, and 7 wagon. And you have the corresponding totals of the subcategories at the right of it. That means in Asia you have 158 variables in total distributed across different types. So similarly in Europe you have 123, in US you have 147. Similarly across the origins, how the different type of vehicles are distributed. You have 3 vehicles in total for hybrid across all the origins, 60 SUVs across all the origins, 262 sedans, 49 sports, 24 trucks, 30 bug. Now this helps in modeling exercises as well. You probably may not want to have a category which is sort of very different from the other categories. It's having, say for example, 94 sedan Asia 94. You probably may not want to have it because it's not very very different from other data sets or observations, but you might encounter cases where the category is entirely different from the rest of the category. So that is an outlier. You probably may want to leave that from the modeling exercise. So the next thing is that how do we plot variables, and why do we need to plot a variable? Okay, so we can plot a variable by using proc plot. Okay, so while using proc plot, make sure that you use the ODA statement. This is a prerequisite. ODA's graphics on. So your graphical features of the SAS program is enabled by when you run this particular code, and then underneath you write a code proc plot data name. Then you can plot 2 variables at one time, right? You cannot just plot 1 variable. So plot 2 variables. I am plotting length versus weight. Okay, and then let's see. how it looks. So you can see in your x-axis you have weight, and then in your y-axis you have only length. Okay, so this plotting is the best way of getting to know your outliers. In fact, when we plot a variable, we get to know about this variable a lot better than having different statistics, because when we visualize the data, it is better to understand it, or you can understand it before passion, and you can get to know which all data points are your outliers, which are not similar to your most of the data sets, which are very different, just like these points, the points at the very rightmost part of the plot. These points can be considered as outliers because they don't really lie close to your average data. But you can see a lot of data are actually clustered from weight 3000 to weight 6000. Okay, so this is a normal data. Probably you may want to get rid of the data sets which are lying greater than 6000, weight 6000, and then greater than length to 220. So all these data sets probably can be considered as outliers, and you may want to remove them from the data sets before doing modeling. Okay, it also helps to know how length and weights are related. You can see that as the length increases, the weight also increases. So we can find that length and weight are very linearly related. If the length increases, so is the weight. Okay, so this is a way in which you can also get to know how the variables are related, whether they are related in a direct way or indirect way, positive way or a negative way. Okay, so a lot of questions can be answered by looking at the graphical plots. Okay, so this is how you do the exploration using graphs. And yeah, so the next thing that we will study is how do we explore data using proc univariate. Okay, so in proc univariate we can obviously use one variable at one time. The name univariate suggests that univariate means only one variable. So um, you can put proc you can put ODS graphics on, because you have some graphs that actually come out of this proc. So you get to see them, but that's optional, it's not compulsory. I mean, you may not you can remove this also, it's not very important. So the syntax is like this: proc univariate data, you give a data set name, and then which variable you want to explore in the var statement, and then run, and then quit. Make sure you put quit in both in gplot as well as in univariate, otherwise it will keep on running forever. So proc univariate actually gives you most of the things that you actually get in proc means. Proc univariate is more exhaustive. It gives you the details, a lot more detail statistics about the variable. You have the number of observations, the mean, the standard deviation, the skewness, and then some of the weights, everything is the most of this important statistics about the data set is available in the output of proc univariate. You need to know what is skewness, what is cortosic. In proc means it's not possible to have skewness and cortosis in your output. So how does it help? If you know skewness and kurtosis, you will get to know whether your data set is symmetric or unsymmetric. So what is skewness, what is kurtosis, what is symmetric, non-symmetric data, all that we'll study in a different video. So I suggest that you read you go through that video first before actually seeing this video, so that you will get an idea about the different the statistical concepts before actually interpreting this statistics. So you have mean, median, mode in the output as well. Range is also there. So range is nothing but the difference between your minimum and maximum. You have variance, standard deviation. Variance is nothing but the square root, the square of standard deviation. And then there is a null hypothesis test that is also there. So what is hypothesis test is something that you will learn in a different lecture. So essentially this is the test to know whether your mean is 0 or equal to 0. Well, you have different statistics, and then the p-value and the t-value suggest that the mean is not equivalent to 0. We accept the alternative hypothesis that it's not 0, your mean is not 0. Okay, so that's a very useful thing. You don't need to do it separately. You get it directly from the output. Then there is a very important thing, the quartile distribution. Okay, so this is very important. You get to know what is the value in the first quartile, the second quartile, and the third. Of course, your second is your median, and then your third quartile, and what is the maximum. Now this helps us also knowing how your data set is distributed, whether it's evenly distributed or there is a very non-symmetric distribution, in the sense that it's very skewed, or a lot of observations are concentrated at one particular area and very few observations are located at other area. So as you can see, our data is quite evenly distributed, in the sense that it goes from the minimum to maximum at a very fairly uniform way. Sometimes you may come across data set where it could be very uneven. Okay, it starts with a small value, then suddenly jumps, and then doesn't increase much, and then suddenly increase again. So that's quite uneven distributions. And then you have details about the extreme observations. This particular matrix helps you locating your outliers also. So you have lowest, your value, and then how many observations are there. You have highest, the corresponding value, and the number of observations there or around it. So it really helps us knowing outliers, and then we can take necessary steps, like necessary measures. Sorry. So the last thing in the lecture is how do we plot a histogram using Proc univariate. So to plot a histogram, we need to use the ODS graphic statement. Okay, so make sure you have it before using Proc univariate. So the syntax is pretty much same, just that you have to put histogram and then the variable for which you want to plot your histogram. Let's run this. It takes time. Yes. So so this is the histogram. This is a graphical plot of the data. So what is a histogram? It's one way of presenting your data in a graphical form. you have different value of the data in your x-axis and the corresponding count in the y-axis. Okay, and how does histogram helps us knowing data set? It helps us knowing the distribution of data across different value. There is another important thing which is very important in statistical analysis. Most of the statistical analysis assumes that your continuous variable is distributed normally, or the normality is a basic criteria. Just by looking at the histogram also, you can get to know whether data set is normally distributed or not. You can obviously plot your normal plot, theoretical normal plot along with histogram. We'll see that in another video. But yes, it looks like it is normal distributed, although it's not it's not a proper way of looking at it. There are better ways of doing it, but it gives you some idea whether it's close to normal or not. Okay, whether it looks like a bell-shaped curve or not. So it doesn't give you a good way of looking at it, but it gives you some way. I mean, in most cases, if you don't have good features in your system, histogram is also good enough to know whether your data set is distributed normally or not. So in that way, histogram really helps us understanding the data better. So to summarize, exploratory data analysis is a must thing before doing any statistical analysis. The techniques are very simple but very powerful and gives us a number of insights which can be confirmed after doing the modeling, but the initial understanding about the data is what we can get by exploring the data more and more before doing any statistical modeling. We can form a lot of hypotheses by looking at the data. Okay, so it gives us an idea, understanding the problem, understanding the data. How do we deal with missing value? What is the count of missing value? Whether my data has outliers or not, whether my data is symmetric or unsymmetric, whether my data is correctly distributed across different categories or not. So all these things we can get to know, and thereby understanding the data better by doing these exercises. Okay, see you in the next lecture. Thanks.
In this video, I'm going to show you how to build a linear regression model using SAS. I'll take a dataset to show you how to build a model. The dataset that I'm going to take is height weight, which has got 4 variables: sex, the age, height, and weight. So we have data for sex, age, height, and weight for each individual. So we will try to build a model which will find out the weight of an individual given his sex, age, and height. Okay, so I'll first run the data statement in order to create a SAS data. So the data is STWT, which stands for the height and weight. All right. Once the data is ready, the first thing that we will do is we'll do a simple exploratory data analysis. In exploratory data analysis, we try to understand the nature of the data before starting to build a regression model. We'll first see what is there in the data. To do so, we'll use the Proc content in order to find out the details of the data. So we'll use Proc content data STWT, which is the name of the data set, run. Okay. Now in the output you can see the details about the data. So there are 22 observations in the data. There are 4 variables, and there are also other information related to data which is given. But we are more concerned about the number of variables, the number of observations, and so on. We have got 4 variables: age, height, sex, and weight. The type of the variables are also given, and also the length is given. All right. So we'll first try to get the summary statistics of all the variables. Okay, so to do that, we'll use proc means data and then name of the data set. We'll run proc means first. All right, so there are four variables. The first one is sex, which is an ordinal variable. I'm sorry, which is a categorical variable, and the categories are M and F, which are characters, right? That's why we cannot get a summary statistics of sex. But other three variables are the numerical variables: age, height, and weight. All three are numerical in nature. Hence, we can get the mean, standard deviation, and minimum, maximum, and so on. So we've got the mean of age, the mean of height, and the mean of weight. We'll also get the standard deviation of that, the minimum value, and the maximum value. The reason why we would like to understand the summary statistic of the data or the variables before going for building the model is that we'll get to know if the data is good enough or not. So what are the information that we can get from the summary statistic? Well, for any variable that should be used in a model, in a regression model, it has to have a non-zero standard deviation. Standard deviation cannot be zero. Now in all three cases we can see the standard deviation is greater than zero, and that's a good thing. A standard deviation 0 or close to 0 is not an ideal variable for its use in linear regression. So what it essentially means is that there is no variation in the variables. It's just a constant, and that is not a good variable for the model. You can also get to know the extreme values in variables, which can cause problems in linear regression. So what do you mean by extreme values? So anything that is just too low or too high, so that could be a problem. Now defining too low or too high is a very difficult thing, but if you are concerned with a particular area and you know what is considered to be an extreme value, you'll be better be able to understand which values can be defined as extreme values. And remember that extreme values should be removed from your data before you go for building a linear regression model, because it's going to give a wrong result or bad result or inefficient result, so to say. So in our data we don't see any issue, except there are few outliers, but we won't remove them because they are not too many. Okay, I've just checked the data before this particular session, so the data is more or less fine, so we can go ahead with modeling. And in case we find some issue while building the model, we will see, we can come back and we remove. So we can you can also remove this data, bad data or extreme values at the time of building model. So just that you have to keep it in mind. All right. As I've said, sex is the one of the categorical variable that we have, and then they've got two categories, male and female. So we'd like to know how many are the male and how many are female in your data set. So for that we'll use a proc frequency data, and what we have found here is that there are 16 females and there are 5 males, and one data point is unknown as to whether it is a male or female. So that is one is unidentified one, and the other 21 observations are identified as male or female. 5 of them are male and 16 of them are female in nature. So 72% of the data is female and 22% of the data is male. This is important to understand the distribution of data across different categories, because if there is a huge difference in the percentage of uh, categories, then you might want to have separate models. You may not have just one model which will be okay for male and female, given the fact that there is a significant difference in the percentage of the presence in the data set, and that's what technically known as segmentation. So you can have two segments of model, one for male population and the other one for female populations. So if they're very close by, let's say they are like 45% and 55%, which difference is not very significant, in that case you may go ahead with just a single model. Whereas if there is a significant difference, we may consider uh, to have separate models. All right. It's also important to know how many of the observations are missing in nature. So it's important to know that, and I'll tell you why it is important. Because missing observations are deleted from the data at the time of running your regression model. So this is something, a feature of your software. SAS deletes the entire row that corresponds to the missing observation. We've got one missing observation in this case, so out of 22 observations, we'll just be missing out on one observation, which will be deleted at the time of running your regression. So at this point of time, you should think about whether you would be fine with this particular deletion thing, or you will replace this missing value with some kind of a missing imputation. So what people normally do is that they assign some value to this missing observation. It could be standard deviation or mean. I'm sorry. It could be mean of the a particular variable which is missing out. But in this case, the gender of or the sex of the particular individual is missing, so we cannot use mean or something like that. Okay, so it is up to you. If you're okay with the missing observation to be deleted, or you want to replace it with a suitable value. If there the percentage is very less, then you may think of just be okay with the deletion thing. Else, if the percentage of missing observations is very high, then you probably have to impute the missing observations. All right. The next step in building a model is estimation. Uh, so we so you're sure about your data now. You understand the distribution of the data. You understand the segments that you will be having in your data, and the next step is estimation. As you know, if you understand a linear regression is nothing but is a linear equation, so to say. In linear regression, you have got a dependent variable and you have got a bunch of independent variable, right? So if you're not familiar with the theory of linear regression, I suggest you to go through the theory first. You can find a video about the theory of linear regression in my channel, and you can also find it in other sources in YouTube or in Google. Just to give you a brief background of what a linear regression is. So in linear regression, we have got we try to find the relationship between a dependent variable with a bunch of independent variable. Okay, so for instance, let's say x is an independent variable and y is a dependent variable. So we try to predict the value of y based on the value of x. In order to do so, we try to regress y versus x, and while doing the regression, we find out the estimates known as a and b. Now, using a and b, we can write an equation like this: y equal to a plus b x, right? So given the value of x, we'll be able to find the value of y. Okay, so normally people use y hat and x hat to denote the variables as estimated variables. So these are estimated from the data. So there is just a slight difference in the notation. So what we're trying to find here is predict the value of your dependent variable. So y is the dependent variable here, given the independent variable. Okay, and independent variable could be one variable or could be a number of variables. Okay, x is your independent variable, you can have a number of independent variables. Okay, the total number of estimates that you're going to have is just n plus 1. So n is the number of independent variable. So the first one is called intercept, and the coefficients or the estimates which are associated with each independent variable is known as slope coefficient. Okay, so this is the basic it's just a basic background of what a linear regression is. And how do we interpret this linear regression? We'll see that once we have the regression equations in place. All right, so how do we write a linear regression syntax in SAS? We use proc reg. So regs stand for regression. So this is a inbuilt procedure in SAS that can be used to do the estimation. Proc reg data, the input data set, and then you define a model. The model is weight equal to height and age. In left hand side of the equation, you have got the dependent variable. In the right hand side, you have the independent variable. Okay, so you can have as many independent variables you wish to have. So what we essentially are trying to find here is that we want to find an equation which will help us in finding out the weight of an individual given his height and age. So that's one thing. So that's one thing that we are trying to find here. The second thing that we are trying to find here is that how is weight related to height of an individual, and how is weight of an individual related to the age of the individual. So for instance, if somebody says if I increase my if my age increases by 1 year, how is going to affect my weight? So that question also can be answered from this particular equation. So let's run this particular syntax, particular set of codes, and we'll be able to get the estimates. Remember, we have got one independent variable, two independent variables in this case. So we'll be getting three estimates: one slope coefficient, two slope coefficients, and one intercept. All right. So when we run this, it's not run properly, so let's run it again. All right, so this is the output from your regression procedure, and this process is known as estimation. So we have estimated. There is an internal algorithm which is written in the background by SAS, which does this estimation. So the algorithm that is being used in this case is known as the ordinary least square regression estimation. Okay, so the OLS, which stands for the ordinary least square regression, is the algorithm which is being used to find out the estimates, which are this intercept and the slope coefficients. So let's go one after the other. So we'll have so many things in the output. Not everything is very important, so we'll only see the important ones, which are very important before you finalize your model. The details about your model will be given first. You have got 22 observations, and one observation is being deleted because it's a missing value, as I've already said in the beginning. Then we will have analysis of variance. In that, what is most important to see is whether the f statistic or the f value is significant or not. So what is significance? Significance is nothing but is just concept which says that your value is greater than 0, or it has some impact. uh, because if something is 0, it has no impact, right? If something is greater than or non-zero, so to say, it has some impact. Okay. um, so so the probability value, so probability greater than f should be less than 0.05 in order to say that the f value is significant enough. Okay, and what does that mean, and why is that important to be significant? It is very important to be it's important, and the first thing that you should see in a linear regression, because if it is significant, it says that the independent variables in the model combinedly impact or combinedly has effect on the dependent variable, or in technical words we say that the independent variables explain the variation in the dependent variable. Okay, or in more layman terms we can say that the independent variables are good enough and they are very helpful in predicting the value of dependent variable. Okay, so this is the explanation. If this particular value, f value, would not have been significant, then we should have simply stopped out there. There is no need to go further down in the regression output if your f value is not significant. So in that case, what should you do? You should ideally go back and add more independent variables or drop some of them, and do such exercises in order to ensure that the f value is significant enough. All right. So the next step, so the next output, which is very important to see, is the R square and the adjusted R square values. Okay. R square values explains the variation in the dependent variable. Okay, so dependent variable is weight. Okay, and the R square value in this case is 74%, right? 0.74, so which is 74.23% precisely. So what it means that the two independent variables that we have used in the model are able to explain 74% of the variation in the dependent variable, which is weight, which is a fairly good value. Okay, the maximum it can take is 1 and the minimum it can take is 0, although sometimes you can get a negative R square, but it has no meaning, right? That's it actually means that your model is totally wrong. So R square normally lies between 0 and 1, 1 being the highest, but normally you won't get an R square value of 1. That means it explains 100% in the variation, 100% of variation happening in the dependent variable, which normally you won't find in a regression model. So there is no thumb rule as to what is a good R square value, but people say, and it differs across different area of study. There are some areas where even 0.2 is considered to be a good R square. There are areas where 0.4 is considered to be a good R square. 0.5 is also considered to be a good R square value. Okay, and 0.7 is definitely considered as a good R square value. The problem with R square is that if you keep on increasing the number of independent variables, it is going to increase. Okay, but having a high number of independent variables or a large number of independent variables is not a good thing for the model, for a variety of reasons, because it is very difficult to explain, it's very difficult to implement or use that model in future, because there's just too many independent variables in place. So it's always good to have a minimum set of independent variables which are the best set for the model. Okay, hence adjusted R square is a slight variation of R square, which can be explained in a similar way, the way we interpreted the R square. So adjusted R square is just a slight variation of R square. wherein it penalizes the uses of independent variables. So the more number of independent variables that one would have, the more difference that you can see between the values of R square and adjusted R square. Okay, so that's a penalty that is levied on the model if it has got just too many independent variables. Okay. So normally people use adjusted R square to be the indicator of a good model. Okay, so ensure you look at the adjusted R square instead of looking at the R square value. So 71% is the percentage of variation that is being explained by the model. Down below you will find the parameter estimates, and that's where we will be able to find out the intercept, the slope coefficients. We have got two independent variables, so we will be having three estimates, right? So we have got parameter estimates, right? We've got intercept, which is minus 181.35. The slope coefficient for height is 4.1. The slope coefficient for age is 1.9, and we'll try to interpret what these values means and how does one explain the model by taking these values. Okay, then right next to your parameter estimates we have got standard error, we have got t values, and we have got p values. So the important thing to look at here is the p value. The p value, as we have already seen here at the very top, while explaining the significance of the F statistics, the p value explains the significance of a particular estimate. Okay, and it has to be less than 0.05 for the parameter to be significant. Okay, if you're not familiar with the theory of statistical significance, I highly recommend you to go through one of my video where I have explained what is statistical significance in great detail. You can also read about it in other sources. So what it essentially means is that the parameter estimate is not equal to 0. It's a non-zero value, and the moment we say the parameter estimate is non-zero, it means it does have some impact, or it does explain something about the dependent variable. And or in other words, in layman terms, we can say that it is very useful. We can use it in the regression model. If it is not significant, what do we do? That is a question. Well, if it is not significant, then we just have to leave it there. We just have to remove that particular estimate from this equation. It cannot be used. It cannot be interpreted. We cannot interpret the parameter estimate if it is not significant. You can find out the significance by looking at t values or p values. They're essentially similar types. P value has to be greater than 2.7. I'm not sure the exact values, but it is, I think, greater than 2.7 or less than minus 2.7 to be significant. Or the best thing is just look at the p value. It has to be less than 0.05. Okay, so this is significant. The intercept is significant. Height is significant. The parameter estimate for height is significant, whereas the estimate for age is not significant because it's 0.3. It should be less than 0.05 to be called significant, but it's not significant. What should we do with age? Well, age will not be part of the regression model. We'll only have one variable and one estimate in this case. Okay, so we'll remove age from this equation. It's not significant, or it's not useful in this model. Or in other words, we can say that age does not explain the variation in weight, or we can say that somebody's weight doesn't get affected by his age. Now one might think that is it intuitive in nature? Well, it is not. That is understandable. Age does matter somebody's weight, right? But after a certain age, the weight doesn't matter, right? Once you are an adult, your increase in age doesn't really affect your weight much. but in the childhood days it does matter. If in your population most of the data points or most of the individuals are already adult, so you don't have people below 20 years or so, you don't have observation or individuals in your data set which are children, and so there is not clear mix of data with children, and then adult data sets. They're all adult. So in that case age doesn't really affect the weight of an individual. That's why it's coming out to be insignificant in this particular equations. Now we have the estimates in place. How does it help in having a final model in place? So we can write this equation as weight equal to the intercept plus 4.1 multiplied to height, and that's the linear regression for this. And once you have the linear equation in place, you can just plug in the value of height and you will find the corresponding weight. Okay, so what we essentially find out is that weight equal to minus 181.3 plus 4.1 into height, right? So given somebody's height, if somebody's height is given, you'll be able to find out his weight. So now this can be used for prediction purpose. You can predict somebody's weight based on his height by having this equation. Now this is just one use of linear regression model, which is prediction. There is another use of linear regression, which is known as inference. So I'll just write it down for you. So there are two things. One is prediction and the other one is inference. So the one that we have built here, weight equal to minus 181.3 plus 4.1 multiplied to height, can be used for both prediction and inference. Prediction is nothing but predicting the value of your dependent variable given your independent variable, whereas inference is trying to find out the relationship between variables. Now what one would be interested in knowing that how is height related to weight in individuals or in the given data set. Now given the fact that height is a significant variable, now we have removed age from this equation. Remember why? Because it is insignificant. Now we can say that height is related to weight in positive way. Why it is in positive way? How can we say that it is related to weight in a positive way? Because the sign of the estimate is positive in this case. That means if the height increases, there is a high probability that the weight will also increase. So that is a positive relation or positive correlation to say. Alright. Another important thing you can also find out from this equation is marginal effect. Okay, so there are three things you can actually find out from this equation: prediction, inference, and the marginal effect. So we know what is prediction, we know what is inference. Inference is just that you try to find out whether the dependent variable is related to independent variable significantly or not, and if significantly, whether in a negative way or in a positive way, right? Whether if the dependent variable, the independent variable increases, whether it has a negative impact or a positive impact. That you can find out from this linear regression model, and which is broadly known as inference. Marginal effect, on the other hand, tries to explain if there is an unit increase in the value of the independent variable, how much does that affect the dependent variable. So if you say, if I increase height by 1 unit, okay, if height is 10, your weight will be something, right? If height is, let's say, increased by somewhat with some amount, what is going to be its impact on weight? Okay, so let's take an example and you will be able to understand. Okay, so If somebody's height, let's say, is 100, you know, 100 centimeter. I don't know whether I don't know the unit measure used in this case. All right. So let's take some hypothetical value. Maybe height is something like, let's say, is 100 60 unit. Let's say, I don't know what is the unit is used here. So you multiply 60 to 4, which is 240, and then minus 180. Okay, so that comes out to be 59. Okay, so the weight of the individual is 59 if his height is 60 units. Okay, now what is the impact when we increase that to 61? Well, the impact is that when when we get the difference of the weight, you'll be able to find out the difference is nothing but 4.1. Okay, and that is the marginal impact or the marginal effect. Okay, if I take an example, that will be better. We can explain it better. Okay, so minus 181 plus 4.1 multiplied to 60, so that's the first one. And in the second one you have got the same thing, minus 181 plus 4.1 multiplied to 61, right? So because we have increased the height by 1 unit, when you subtract the second minus the first, what you will be getting, sorry, this will be 4.1. Okay, so what you will be getting is 4.1, right? Because this gets cancelled, so what remains is 4.1 multiplied to 1 multiplied to 60, 1 minus 60, which is 1. So 4.1 multiplied to 1 equal to 4.1. So the slope coefficient of an independent variable is the marginal impact of that particular variable on the dependent variable. Okay, so if you increase weight by 1 unit, the corresponding weight that will increase in the individual is 4.1 unit, and that's known as marginal effect. Okay, so these are the three things that we intend to find out through building a linear regression model. Now there are different aspects of linear regression model. In fact, I will go on talking about linear regression for number of hours. There are just so many things associated with linear regression, and it's not that simple. So just writing a proc reg data statement and defining your model is not enough while building a linear regression model. It's not that simple. There are so many issues one would find or one would come across while building such a model, and these issues has to be dealt with while building a model. So it's not that simple, as I have said, and one has to get into the details of the issues related to a linear regression model. And there are variations of it also, in the sense that you probably have more number of variables, and the moment you have more number of independent variables, you will have problem dealing with them. Okay, and there are so many issues that one would come across while building a model with so many independent variables in place. So we'll see a few of them. It's not it's not possible to just have look at all the problems that one will be facing. I'll just take one or two of them. Okay. One issue one would come across is that the problem of multicollinearity. Okay, so what is the problem of multicollinearity? Well, the independent variables that we are using may be very correlated with each other, right? Like height and age, they may be correlated with each other, and if you keep on adding more variables, there will be higher chances of correlation between one or a number of variables. That is a problem in linear regression. If the variables are highly correlated, then the standard deviation that you are getting in the model output will be not correct, Okay, and standard deviation is very important in an estimate because that gives you the confidence level, right? Okay. So if you go back to your model output, you have the standard error, right? Standard error uh, uh, is in somewhat, it just plus and minus, or it just it's like 4.1, right? So it's 4.1 plus 0.77 or 4.1 minus 0.77. It gives the confidence level, right? So that will be biased in case you have got highly correlated independent variable, and that problem is known as the problem of multicollinearity. So you have to identify this problem before finalizing your model. How do you do that? If you don't know, if you want to learn the theory of multicollinearity, you can watch one of my video where I have explained the problem of multicollinearity, and I have explained how to detect it, how to remove multicollinearity in great detail. Okay, so one of the way in which we detect multicollinearity is through use of variance inflation factor. So we use the keyword VIF, which stands for variance inflation factor, which is very useful in terms of finding out whether or not there is presence of multicollinearity among the independent variables. In one of my video, I have explained in great detail what is variance inflation factor, how does it is calculated, and how does it is related to the problem of multicollinearity. Okay, you can watch that video. Alright, so if you use this option and build the model, you will get the corresponding value of VIF. Okay, let me run it again. The corresponding value of VIF, and through some threshold value, you will be able to know whether there is presence of multicollinearity or not. Now you can see the variance inflation factor wasn't there previously. Now it is there in your model output. So we have got the VIF for intercept, for height, and for age, right? The rule of thumb is that the VIF should be less than 5 for it to be for you to be confident about the fact that there is no multicollinearity. If it is greater than 5, then there is presence of multicollinearity. So that is the threshold people use. Okay, so VIF should be less than 5 for each for each independent variable, right? If VIF is greater than 5, then you have to do a more deep dive or more detailed analysis of independent variables, and if one or more variables are highly correlated, you just have to drop one of them, the less important variable from the model, right? So that's the way you can deal with VIF. So that's the way you can deal with the multicollinearity problem. Okay, you just have to drop some of the variables if there is presence of multicollinearity in a model. We don't have this issue in this case because it's less than 5 in our case. Alright, so this is one problem. The other problem that one would come across in linear regression, one is the problem of heteroscedasticity and the problem of autocorrelation. I'm not going to talk about these problems. They're a little more complicated, and I'll take these problems in a separate video, in another video. In fact, in some of my videos, I have explained about these problems in great detail. You can go through these videos. I'm going to show you another aspect of linear regression in SAS. So you can save the model output in your database. Okay, so for that you just have to use the keyword outtest and just provide the name of a dataset wherein you have you want to save your dataset or save your model output, so that you can use the model output in future, right, for finding out the future weight of individuals given their height, right? So that's the way you're going to do it. Okay, so you use the outtest values wherein you want to save your model output in some kind of a dataset. Alright, now we'll be using the third independent variable that we saw in the dataset in the beginning, that is sex. So we've got two categories. male and female. So we might want to have separate models. So we might want to have separate models with respect to gender. One, as we have said in the beginning, if there is a great difference in the percentage of presence of male and female population, it's always good to have two models instead of just one. So in that case, you use the by statement. Okay, so you just use the by statement and it is going to give you multiple, two models. It can have more than two also if your variable or the categorical variable that you are using the by statement has more than more than two categories, right? Also, you can have multiple linear regression equation in the same statement. You don't have to write as another model statement in order to test multiple linear regression model. Let's say you want to have weight, height, height and age in one model and only height in the second model. You just have to write the keywords equation 1 and equation 2 and then define the model, and it's going to take care of both the models. So in this particular statement, we are seeing two things. First thing, we're going to have two models with respect to sex. So we'll have one model for male and one model for female, and we're also testing, or we are also estimating two models in just one sex statement. Okay, so there are two things we are trying to do here. Is there some error? Okay, so it says that it's not sorted. So what you need to do is that every time you're using a by statement, make sure that you are sorting the data set before using it in the regression. So you just use proc sort and then that will be sorted. So just sort the data with respect to sex. Okay, perfect. Now we will run this and then should not be an issue. Alright, now in the output you can see that you have separate models for male and female. You can see equation 1, because we have got two equations binded. So equation 1 and then sex here is female. So we have got 16 observation in the female population. So using that many number of observations, that is the model has been built. Okay, in the next output you can see the equation 2 has been built. In the population, sex is equal to female. Okay, then equation 1 with sex is equal to male, and then equation 2 with sex is equal to male. Right, so in total you have four equations, four models, right? Model 1 male, model 1 female, and then model 2 male, model 2 female. Right, so you can test or you can build several models in just one equation. So this is just one feature of SAS that I was trying to show here. All right, now is it all fine, or do we have to do more about linear regression? Every time we build a linear regression, you cannot finalize a model without doing some kind of a validation. So validation is also known as testing your or diagnose your model. Okay, so you have several diagnostic statistics in order to ensure that your model is sound enough or good enough. There are various ways you can do it. Okay, if I've gone through some of my other videos, you might have come across cases where I have training sample, validation sample, and then building the model in training sample, validating in in the validation sample, and so on. You might have come across cases like bootstrapping or resampling techniques. I'm not going to use any of these techniques in this particular case. This is a simplest of the model that I'm showing here. I'm not going to give you more complicated way of validating models. So what you can do in validating a model to ensure that your model is sound enough is that You just have to plot some of the test statistics and see if they're good enough. Okay, so for that we'll use the ODS statement, ODS graphics on, and below that we have just written ODS graphics off. So when you run your regression with ODS graphics on, you will get so many plots which will help us validating the model. So let's see them. Things not run properly. All right. Now you can see the plots, right? Several of them. You can get the residual plots. Okay. So if you're familiar with linear regression theory, you must know that the residuals or the error terms in the linear regression should be random in nature. There should not be any pattern in the error terms. If you plot the error term with respect to the dependent variable, then it should be completely random, right? And there should not be any pattern, and they should be very close by, or they should be uniformly distributed across the negative side of the x-axis and the positive side of the x-axis, right? So that's the residual plot you can see here. Now you can see in our case there is no pattern. We can see that the error terms are pretty random in nature. There is no pattern. If there would have been some pattern, then there is something wrong with our model. You may have to revisit your model. You may have to ensure that your your diagnosis of the model in terms of finding out multicollinearity, autocorrelation, heteroscedasticity are well dealt with before finalizing model. So that's very important. In our case, that's not an issue, except just one issue. You can see an outlier in this case, right? So this is just an outlier. It should have been removed before we build the model. But this is one case, this should not make a lot of impact. But you may want to, and it's always advisable to do so, you may want to go back and remove that variable and run the regression again and see if there is a significant impact in the estimate. If there is a significant impact, then you should remove this particular observation from your data. So that's an outlier. So you can find out some of the outliers from residual plot and just remove them. Except that we see no pattern in the residuals, and it's all randomly distributed, and it's distributed in both sides of the x-axis. So that's fine, perfectly okay. So there's no issue with that. Another important thing you might want to see here is whether the error term is normally distributed or not, right? So we might have come across the assumption in linear regressions. One of the assumption is that the residual should be normally distributed, right? And you can see the residual is somewhat normally distributed. So that looks normally distributed. If you remove this outlier, I'm sure it will be even very closer to normal distribution. So that is that will be very good then. Okay, so these are some of the diagnostic statistics that you should look at before finalizing the model or before signing off. Okay, so as I've said, these are the steps one has to perform. These are the basic steps. Even I would even say there are more steps to be followed for building a model, but these are the bare minimum steps one has to follow in building a linear regression model. Linear regression model can be used for several purposes. As I've said, it can be used for prediction purpose, for inference purpose, and for knowing the marginal effect of independent variables on the dependent variable. This model can be used for prediction of values for dependent variable and for policy making purpose, through finding out the relationship between variables and through finding out marginal impact on the dependent variable. Okay, so that's all for this particular session, and in the next session we'll learn more about the more aspects of linear regression through autocorrelation, heteroscedasticity, and we'll also see how we can use sampling techniques to validate models. So see you in the next. In this video, we are going to learn how to build a logistic regression model in SAS. If you know what logistic regression is, you must be knowing that logistic regression is type of regression model which is used for categorical dependent variable. This is very popular in cases where the dependent variable has got only two values, or technically speaking, the dependent variable is binary in nature. Well, it's used in many industrial and academic applications. One of the most important important use of logistic regression is in the field of credit scoring, which is used by most banks and financial organizations. So we will learn how to quickly build a logistic regression in step by step. So I'll take an example and that's how we're going to learn. So here is an example. We're going to data which is having the student's performance and whether a student is getting admission in a college. Okay, so the dependent variable for us is this one, the one I have highlighted. It's admit. The students have applied to different universities, and whether a particular student get admission in the university depends on various factors. The factors could be his GRE score, his GPA score, the rank of the university, the undergrad university which the student attended. So these are some of the factors that could affect the student's admission to a particular university. Right? So we'll try to predict if a student is going to get admission in a particular university or not based on his GRE score, GPA score, and the rank of the university that he attended for his undergrad education. You can see that the dependent variable has got only two values, 0 and 1. So if he gets admission, we have said it that we have denoted it as 1. If it doesn't get admission, we have denoted it as 0. So that's just a denotion. You can actually put any value. You can put 1 for admission, 2 for not getting admission. It's entirely up to you to use any notation that you are comfortable with. So the idea here is to find out what is the probability that a student is going to get admission in a university. And as you know, to model for probability of an event or probability of happening something, logistic regression is probably one of the most popular modeling algorithm used. So the first thing we have done is we have just imported the data from my desktop, and so first let's try to run proc content, where you'll get to know what's exactly is there in the data. So it's going to give us how many observations are there in the data. We have got 400 observations. There are 6 variables, but we are going to use 4 of them. Yes, the variables are admission. This is going to be the dependent variable for us. GPA score, GRE score, and rank. These 3 variables are going to be the independent variables. Now the last 2 are the ones we have created, so we'll make use of them later on, but not in the beginning part of in the first part of this session. Okay, let's try to understand in the data how many of them have got admission. So we'll use a proc frequency for that. So in the data we have 127 students who have been able to secure an admission in the university, and 273 who haven't been able to get admission. Now remember, this is the data that we have with us, for which we know for sure that whether a student has got admission or not. But the model will not be used for this data. The model will be used for a completely new student, for whom we have not actually the value of his admission, or we do not know actually whether the student is going to get admission or not. We'll predict the probability of him getting admission using this model. So that's the idea. So this is just a historical data, or the data that we already know, or the outcome of the model is already known to us. Okay, so these people have already got admission, so we know for them, so we have got some sort of a value for the dependent variable. Okay, so we call this data as a training data. Okay, little more analysis on the data. You should actually do more analysis. I'm going to limit it to only means, but you probably should do univariate analysis as well on the data and see whether the data has got outlier, the data has got good distribution of a good distribution for the model to build. Okay, so what we can see is that 31% have got admission. So it's a 31% to 69% distribution for 1 and 0, which is fairly a good distribution. Ensure that the event in this case is 1, because we are interested in getting admission and we have denoted it as 1. So ensure that the percentage of 1 should be sufficient enough, at least 2 to 3% or 4%. Anything below that is bit of an issue. Then we have got the independent variable. The average GRE score is 587. The minimum is 115. Sorry, the minimum is 220 and the maximum is 800, and the standard deviation is 115. Now this is one thing that you should remember, that the standard deviation should never be 0. If the standard deviation of an independent variable is 0, then that's a problem. You cannot use that data or use that variable in the model building process. Why is that so? Because if the standard deviation is 0, which means that there is no variation in the independent variable, and that's not a good thing. If there is no variation in the independent variable, it is not going to help you predict your dependent variable. So that's the idea. So all you need to do in this case is just drop that variable from the analysis. So ensure that your standard deviation is always non-zero, and the more it is, the better the variable is for prediction. The GPA score average is 3.3 and its standard deviation is 0.38, which is non-zero, which is good. Rank is anyway is a categorical variable. It's not a continuous variable to say. So mean of rank won't make much sense. But all you need to know what there is a good variation of rank. We have got minimum of 1 and maximum of 4. So for rank variables which are categorical in nature, or variables which have got ordinal in nature, it's always good to do a proc frequency in order to understand the distribution instead of proc means. Okay, so I would encourage you to do a proc frequency of rank in this case. Okay, we can actually do it. Okay, we can actually show it to you whether there is a good distribution of rank. You can see that yes, 15% of people have come from rank 1 university, 37 from rank 2. So pretty good distribution. So it's a useful variable, so to say. Okay, let's straight away go to building a model. Now remember one thing, in real scenarios, there are many things that you do before you actually go ahead with the modeling. But here the purpose of this tutorial is to make you familiar with the basic logistic regression and how you interpret a logistic regression and how we use a logistic regression in practice. But you actually do a lot more before you get into a modeling process. The steps could be analyzing your data, removing some of the observation, finding out which independent variables are good enough, dividing your data into training and test sample, or training a validation sample. So that's another important thing. Build a model in training sample and test your model in validation sample. So these are some of the exercises you do. You do sampling as well. You find out a best sample which would represent your population, and many more things. But we will only limit to understanding a logistic regression without going into the details of the other things that you actually do before building model. We'll see that in another tutorial. So we'll use the student data. The syntax is like this: proc logistic data, and then you provide the name of the dataset, and then you provide what is known as descent, DESC. It's a keyword you use because by default proc logistic model for 0, but we are interested in 1 in this case, right? We are interested that if a student is going to get admission, now 1 is the is the value of interest in independent variable. And what it does, proc logistic always takes the ascending order. That means it will always model for the lowest value among the values in the dependent variable. So the values are 0 and 1 in the dependent variable. So if you do not use DESC descending, then it is going to uh, it is going to build a model for 0 probability of getting 0, not 1, but we are interested in 1. So always use descending if you are interested in finding probability of 1. Okay, so we are talking about 1 and 0 in the dependent variable, so don't confuse with that. Alright, so we are also using class statement in this case because rank is sort of a categorical variable which has got 3 categories. So we want that these categories should be taken into consideration, and we are saying that rank is a categorical variable which has got 3 ranks. So we'll get 3 estimates for the variable rank in this case. If you do not use that, you won't get 3 estimates. You will just get 1 estimate for for rank. It is going to be considered as a continuous variable, which is not the case, right? So it's always good to use the class statement if you have a categorical variable in place. The model statement is like this. Now this is the most important and something that, I mean, you cannot have a class statement, that's okay, but you should always have a model statement. That's where you define your model. So left hand side you put your dependent variable admit and then equal to, and in the right hand side put all the independent variable that you are interested in. Now you may not be interested in all the independent variables that you have in your dataset, but in this particular example we are using all the independent variables we have in the dataset. So we are not dropping any one of them, but we might do that when you actually run the model and see some of these variables are not good enough for the model. We'll see that later. There are a few more things we should also mention here. So once we have the model in place, we want to save the probability against each one of these observations in a data set, and we are calling that data set as out data, and you can give any other name. Okay, up to you. So what we want to save, we want to save probability, and we just give that as a name, predict under probability. We also want the lower and the upper limit of that probability. Now in any statistical estimation you always get a lower and upper limit, right? That's the confidence interval for you. So we also want that to have, just to understand how the probability is distributed within its lower and upper limit. So we're all ready. We are all set. We'll just run this code. All right. So next thing that we'll do is, we have the output from the logistic regression. The next thing that we're going to do, we'll just understand each one of these steps. There are many things that SAS will provide you, but we'll go through only the most important ones. Okay, initially you will have which optimization technique has been used. I mean, there are some default techniques that SAS uses. If you want to specify any technique, then you can specify. But normally you will find that most optimization techniques are going to give you pretty much the same model. There will be hardly any changes. So you need not worry that. So here we SAS has used Fisher scoring, which is by default is used. So number of observations rate and use both 400 and 400. Now this is important. What happens is that sometimes your data has missing value. If one of the data point in any one of these variables, dependent or independent, is missing, then the entire row will be deleted, or the entire row will not be used for the estimation, or that particular row will be completely ignored. So if you have data with missing values, your number of observation used will be less, that very less number from the number of observation rate. But in our case, we do not have missing data, so all the data that we have provided is being used for estimation. Then we have response profile, wherein you have the categories. In logistic regression, you always have two categories. We have denoted at 1 and 0, and there is sufficient distribution, a good distribution rather, for it to estimates for the probability of getting 1. Now we are interested in probability model admit equal to 1. So what is the probability that a student will get admission in university? So we are interested in probability admit equal to 1, and that's exactly what is the output giving us. Now remember the DSE statement that you had I talked about for a while. If you do not use that, here it is going to be admit equal to 0, but we are interested in 1, right? We are not interested in somebody not getting admission, we are interested in somebody getting admission. So ensure that you use the statement DSE in the Proc logistic. Then make sure always see the model convergence status. Many times you do not get a converse model. If a model is not converse, or it doesn't converge, then you cannot use the model output. You will get some sort of a model output, but that won't be the optimal model output. So you have to go back and do a lot of other things before you can actually get it to get the optimization routine to converge. In this case, the model conversion criteria is satisfied, so we are fine with, and we should be having an okay model, or rather the model that we are getting can be used. The next table you get is model fit statistics. The three important statistics that you get: one is AIC, known as Akaike Information Criteria. The second one is Squares Bayesian Criteria, SBC, and third one is the log likelihood, right? Log likelihood value. Okay. So the idea here is that you should, I won't get into the details of what this, what the statistics are. You can always learn what is Akaike information criteria, what is Squares Bayesian criteria, but make sure that if you have multiple models, make sure that the one with less AIC, SBC, or log likelihood value is your best model. Now the idea here is that if you use too many independent variables, you will probably get a good model, but your AIC value and SC value will go up. So having too many independent variables is not considered to be good for the model. The model will be overfit, the model cannot be used efficiently for future data. Hence, AICSC penalizes you for that, penalizes you for having more number of independent variables, and hence your AIC and SBC value will go up when you use more number of independent variables. So that's one statistic you look at. If you have multiple models, just compare them and see which one of these model is giving least AIC, and that's exactly is the model that you should go ahead with. The next one is the global null hypothesis. Now this is a null hypothesis which is like all the beta parameters in your logistic regression are 0. The alternative hypothesis to this null hypothesis is that at least one of the beta parameter is non-zero. Now intuitively, what does it mean? Well, it means that the independent variables used in this model are able to provide you better results than a random guess. Okay, so it says that independent variables are of some use, they cannot be ignored. Okay, if this is not true, then there is no need to go below. If your null hypothesis is not rejected in this case, or rather in other words, if the statistic likelihood ratio test, score test, or wall statistics, they are not all significant. In this case we have all, all the statistics are significant because the values are less than 0.05. You can see the p values. The p value for likelihood ratio test is less than 0.05. Same with score stat, same with the wall statistics. If this is not less than 0.05, your global null hypothesis will be accepted. That means all betas are 0. So there is no point in building a model, rather going ahead with other statistics. You have to stop, go back and rebuild the model again, because it says that none of the independent variables are good enough for the to predict your dependent variable. But luckily we have all three statistics significant, so we are good. The next important and the most important is the analysis of maximum likelihood estimates. The algorithm used to find out the estimates in logistic regression is maximum likelihood estimation algorithm. Hence, we get we call these as maximum likelihood estimates. So like any linear regression, you get intercept and slope coefficients. The intercept is in this case minus 4.88, and the slope coefficients, there are remember there are 3 independent variables, so we will get as many slope coefficients. However, one of the independent variable is a class variable. Okay, so if it's a class variable, you would get that many number of additional how many number of classes are there? 3. So we'll get 2 more estimates. So if there are n classes, you'll get n minus 1 more estimates, and we'll see why is it so. For GRE, we have got the estimate as 0.00226. For GPA, it's 0.8. For rank 1, it's 0.89, for rank 2, 0.21, for rank 3, minus 0.44. What is important to see here is the p-value of all the statistics. Now ensure that for the p-value to be significant at 95 confidence level, it has to be less than 0.05. Here it is the case, it's less than 0.05, so significant. Less than 0.05, GPA is also significant. Rank 1 is also significant. Rank 2 is not significant, and rank 3 estimate is significant. So we are interested only in the cases where the variables or the estimates are significant. Insignificants are always going to be ignored because they are not significant. All right, the next important thing to look at in the output of logistic regression is whether the model is able to do a good job, or there can be a better model. So we'll look at what is known as association of predicted probabilities and observed responses. So here what is important to look at is the percentage confidence and percentage discordant. So if you have higher percentage of confidence, the better is the model. Okay, And what we usually look at is the C value, which is also known as the concordance statistics or C statistics. It is 0.693 in this case. A few things to remember about the C statistics. The C statistics has to be greater than zero point 0.5 all the times. It cannot be less than 0.5. If it is, then your model is totally wrong. It performs very bad. Why? Because in a binary response variable, if you toss a coin or you randomly choose, you will most likely get 50% of the times correct. So if your model is doing worse than that, then your model is worse than even random guess. So your model has to be greater than 0.5 to be called a good model. But and concordance statistics, C statistics always normally lies between zero point 0.5 to 1. The closer it is to 1, the better is the model. So getting a bigger or higher C statistic is always good. So in our case it's 0.69. So we might do something with the model to get a better C value. The some of the ways are including new variables, include transform variables, doing the including polynomial terms of the variables, and see if the C statistic is going off. If it is going off, then the model is able to do a better job, and the one with highest C statistics should be the one that should be used as the final model. Okay, now we have saved the output in the out data. So let's go to the work folder, and that's exactly where I have saved. But you can save it in any place. You can save in your own folder as well. So in the output, we have the estimated probability, lower confidence, and the upper confidence. Okay, this is estimated probability. So against each and every observations in the training data, you have a probability. Now, what we would be expecting is that wherever we have admit equal to 0, the probability should be less than zero point 0.5, because that's the middle probability, right? Anything greater than that, we should have a 1. Anything less than that should have a 0. If that's happening, then that's a good thing. Otherwise, it's something is wrong, or rather inefficient. So here it is right. Admit it 0 and probability is less than less than 0.5. But it gets wrong in the second one, because the probability of admission is 0.2, but the person gets admission. So that's the wrong prediction. And it can happen. In model, you cannot get uh, right all the times. The next is the probability of getting admission is 0.73, which is greater than 0.5. So your probability chances are that the student will get admission. That's what the model says, and you can see that yes, the student has got admission. So it is a correct prediction. So there will be correct prediction, wrong prediction. You can actually do a tabulation and see how many times you are getting correct prediction and how many times you are getting wrong prediction, and we call that as accuracy test. Okay, you can do it by yourself. I'm not going to do it here, but you can test greater than 0.5 and admit equal to 1, how many is there, less than 0.5 and and admit equal to 0, how many are there. So that's your correct prediction, and rest everything else is just a wrong prediction. And just see what is the percentage of correct prediction and what is the percentage of wrong prediction, and the objective should be to increase the correct prediction. All right, now the next thing, now the important question, and many students have asked me this question, that all right, you have the model in place. Now the model is able to give you the probability value, but how do you use it? Well, the model that we have just you know uh, we have just seen here. So model is nothing but just equation, right? So if you're familiar with the logistic regression equation, it is just a logarithm of p by 1 minus p equal to beta naught plus beta 1 x, where x could take many independent variables, and you have got the estimates. Just put the estimates and you will find the probability value. And that's exactly how SAS has been able to find out the probability for each observation. You can do it by yourself also. And I'll encourage you, write the logistic regression equation, put the estimates value, and find the probability value. You can find it by yourself also. Now, for a completely new student, for whom you know the GRE score, GPA score, and rank, just put the values of this, use the estimates, and find the probability. If it is greater than 0.5, predict that the student will get admission. If it is less than 0.5, the student is not going to get admission. Okay, and if it is exactly zero point 0.5, then the conclusion is that it's ambiguous. It's not very clear whether the student is going to get admission or not. That's the way you use a model to predict something totally new. All right, as I've said, you can actually improve this model by including more independent variables. You can use many other statistics if you have the access to the data. It's not just a GRE GPA that matters, it's also the other things, right? That could be let's say the admission is on engineering subjects, so it's the marks on mathematics in undergrad will matter a lot, mathematics or science. Okay, just put that as a variable. The second other thing, among other things, could be score on language subjects. Does that matter in getting admission or not? Extracurricular achievements and so on. So if you have access to more independent variables or more data, just include them. If you do not have, then do transformations of whatever data or whatever independent variables you already have. Just do transformations. So we have done one transformation here. We have just you are using a polynomial terms. We are squaring the GRE and squaring the GPA, and we're calling it as GRE2 and GPA2. You can do any number of transformation, logarithmic transformation, exponential transformation, and so on, as long as you are comfortable with with explaining this variables. So we'll just run this, and we'll include this new independent variables and run the logistic regression again. So what is important here is to see whether okay, make sure that you close the data set. Do not open it and run. That's not going to run. Anyway, we already have that in students, so we can directly run it. No worries. So what I was saying is that ensure by including more variables, look at the C statistics. It should go up, but ironically, it has gone down, and it can happen actually. So adding more variables or adding polynomial terms in this case is actually not helping us. In fact, it is reducing the efficiency of the model. So it is better not to use them. Or maybe you can try other transformation like logarithmic transformation, exponential transformation, and so on, and use in the model and see. So you just have to go back and forth and try all your use all your creativity to find a better model. And there is no thumb rule as such what exactly is the best model. Just try all sorts of things, do transformation, use polynomial terms, use different algorithms, and you will come up with a better model. The second thing that we're going to see is model selection in logistic regression. In logistic regression, you have many ways of selecting a model, and one way is finding out a set of independent variables which are very good for the model. Some of the independent variables are not so good, and they should be dropped out from the model. So there are a number of variable selection statistics, variable selection algorithms that comes along with logistic regression, and it's also there in SAS Proc logistic. So one of the way is forward selection. The second one is backward selection, then stepwise and score selection. I won't get into the details of what the selection, how the selection of variables happens, but these are some of the selection that you can use. Okay, in some if I were to tell you in brief what the selections procedures are. The selection procedures take one variable at a time, okay, and see whether that is useful to the model or not. If that is useful, then they retains it. Otherwise, the algorithm is going to drop the variable. So that's the idea. So to the syntax, you just add this one, selection, and you can specify what is the entry criteria and what is the stay criteria. It's entirely up to you, but it's always good to go with the default entry and stay criteria. Selection is forward, it could be backward, stepwise, or scope. So let's go ahead with forward and see what is forward selection, and how do we how is a forward selection logistic regression is different from a normal logistic regression. Now you can see there are many steps in which the variables are selected. So this is step 0. Only the intercept is there. Okay. In step 1, only first variable is used. Rank is used. Okay. The second one, and by the way, the most important variable will be entered first. In the step 2, GPA is used. Okay. In step, so you have rank and GPA with the model now. In step 3, GR is entered. So now you have all three variables. Okay. Then when all the important variables are included in the model, then you will get your maximum likelihood estimates. Now there are sometimes what happens is that some of the uh, independent variable do not satisfy the entry criteria. They do not enter into the model because they are not considered to be good enough using some sort of a statistics, and the statistic used in this case is the chi-square statistic value. If that is the case, you do not quite use that in a model, that gets dropped. And we have only three variables which all are important ones, so it's all entered in the model. But if you have like 10, 15, 20 variables, some of them will get dropped in the process. You can use a backward also. Backward is just the opposite. It starts with all variables. Okay, sorry. It starts with all variables and it drops one after the other based on the importance of variable. That's right. So it started with all thing intercept, GRE, GP, rank. Remember, it's exactly the opposite. In forward, it started with just intercept, then GRE, GP. It went one by one. It started with intercept and then one variable, two variable, and then three variables. In this case, it's exactly the opposite. It starts with all three variables and it drops based on exit criteria. But here all three are significant, so it doesn't drop any of the variable. Just finds out the final estimates. Okay, so that's how you can build a logistic regression model. One of the exercises that you can do is use the same data and you can find the data. You can get the data in the description section of this video. You can get the access to this data. You can also get the code that I have used in the description section, and you can use this data. And the exercise that you should be doing is, we have got a C statistics of 0.693. That's the best. Can you increase that? Can you increase to, let's say, 0.72 or 0.73 or so on? Just try all sorts of combinations of independent variable and see if you can increase the predictive power of this model. Thank you so much.
Hi, in this video, I'm going to show you an example to understand what is ordinal logistic regression. So I'm going to take a data set to do that. So here is the data set. So let me explain you what the problem is. So I've taken a data set that has the rating of different cricket players, and there are various categories of cricket players we have taken into consideration. Okay, now the idea or the problem that is given to us is that to find out the probabilities of a certain player getting a certain rating. Okay, and there are 9 categories of rating. You can see there are 9 ratings from rating 1 to rating 9, rating 9 being the highest rating and rating 1 being the lowest rating. And we have categories, so different categories of cricket players, and I'll explain what these categories are. Okay, so the first category is the Indian international, so Indian cricket players who is part of international team. Then foreign national, because in Indian Premier League there are also foreign players who are also participating. So foreign cricketers who are also playing international cricket are in the second category. Then the Indian domestic, so players who are playing in the domestic league, and they are from India, third category. And then foreign domestic. So these are the 4 categories. So we need to know, based on these categories, who's the likelihood of someone getting a particular rating. And there is also frequency, like from how many players we have found out this rating. So rating is the target variable for us, and category is going to be the factor or the feature or the independent variable which will give us an idea of what's the odds of someone getting a given rating. Okay, and frequency is like the number of players who have been taken into consideration uh, to come up with this rating values. Okay, so we're not going to use frequency, we'll only use a single independent variable. And the idea is to understand the ordinal logistic regression. Now, what is logistic regression? Well, if you're familiar with logistic regression, you know that it's a type of regression used to model categorical data. So if a target variable is categorical in nature, it has dichotomous, that means it has got 2 values. Most of the times it's 0 or 1, and they're trying to find out the probability of your target variable taking 1 or 0. So that's where you use logistic regression. Now, ordered logistic regression is an extension of logistic regression to multiple categories. So not just 2 categories or not just dichotomous. You can have multiple values for the target variable. Now, the values should be ordered. That means they should be in certain order. You can uh, have these ascending order or descending order. For instance, the rating of players from 1 to 9 are in the ascending order. That means rating 1 is the lowest rating, and you can go up 1 to 2, and that's higher rating, and then 3 much higher rating, and up to 9. So they can be ordered. So rating can be ordered. So a case is where you have more than 1 category, more than 2 categories. So here we have 9 categories, 9 types of rating, and they can be ordered. In that case or in those scenarios, you can use ordinary logistic regression. So I'll just repeat. The target variable should have multiple, more than 2 categories, and the categories should be in ascending order or in descending order. It should be in some order. Okay, you can have an ascending order, descending order. In such a scenario, you can use ordinal logistic regression. Now, one of the assumptions of ordinal logistic regression is that there is assumption of proportional odds. Okay, I'm not going to get into the details of what proportional odds are, but from a prediction point of view, that assumption is not that relevant. But from, if you want to explain, if you want to understand how your independent variable affects your dependent variable, then that assumption is quite important, and it's important to know whether proportional odd assumption gets validated in this case or not. Okay, so I'm going to straight away go build a model. Okay, I'm going to build the model. So I have shown you the data. So we have got this as the dependent variable rating, and categories as the independent variable. The syntax is similar to what we have seen in the logistic regression, proc logistic data, and then I'm going to use the data set players. That's the name of the dataset. And we have class information. So category is it's a class variable, so we'll have these classes. And the reference category is 4. And explain what reference category is. That means when you will have the result, all the rest of the categories will be compared to the fourth category. So fourth category is nothing but the foreign players, right? Foreign cricketers, foreign domestic cricketers. So they are going to be compared with all other categories. Model is y is nothing but your rating, and then cat is the category. Okay, that's the only independent variables. Okay, so we'll run this, and I've already run this. I'll straight away go to the results. Let me show you how to interpret the results in a ordinary logistic regression. Okay, so you have 36 observation, out of which 28 have been used. So 8 observation have been removed. They may be having missing values, so that could be the case. So there are 9 categories in all. Okay. So total frequency, that means frequency will be used as a count. So frequency will be multiplied to the number of times it appears in the dataset, and that's why it is total frequency, and that's the numbers. And then we need to see whether the convergence criteria has been met and it's satisfied, so we can be sure that the result is good enough to interpret. Otherwise, if this would not have been satisfied, then we cannot go ahead in understanding or interpreting the result. Alright, so we also need to look at the global null hypothesis state. It has to be significant, otherwise you cannot explain or you can interpret the result. So this has to be significant. So all the p-values are with the given less than 0.05, so it's significant. So okay, now we will go to the analysis of maximum likelihood estimation. So ordinary logistic regression, much like other logistic regression, uses a maximum likelihood estimation procedure to get the parameters. We have got several intercepts. Why? Because we have got several categories, right? So for categories, we have the estimates, the beta estimates, and the corresponding p-values. Now all are significant, as can be seen here, less than 0.05 in all cases. Okay, so what's important here is to understand what's the odd of somebody getting a lower rating and higher rating. So the idea is to understand somebody belonging to a particular category. Let's say somebody is from a foreign domestic player, how his chances of getting a lower rating is compared to someone playing someone from Indian domestic player. Okay, or somebody who is international Indian international player is compared to a foreign international player. Okay, so we can do this comparison. So category 1 to category 4, that means Indian international player has been compared to foreign domestic player. Okay, so the odds of Indian international player getting a lower rating compared to the foreign domestic player is 5.05. Similarly, the odds of the foreign international player getting a lower rating compared to a foreign domestic player is 143. Somewhat okay. And then category 3 compared to category 4, that means an Indian domestic player getting a lower rating compared to a foreign domestic player is 27.734. Okay, and then the C statistic is 0.789. The better the C statistics, it is the better the C statistic, the better is the model. So it normally lies between 0.5 to 1. The closer it is to 1, the better is the model. You can also look at all the comparisons. We look at, as I've said, 4 is the reference category, and in fact you can change the reference category. If you see the code, we have used the reference category this as 4. We can have the other categories as the reference category as well. So okay, so we can see the all the combination of categories. So cat1 to cat2, cat1 to cat3, cat1 to cat4, cat2 to cat3, cat2 4, and then cat3 to cat4. So all the odd ratios have been estimated, and we have also the confidence limit for the odd ratios. Okay, so odd ratio gives an idea about, so somebody belonging to category 1, what is the likelihood that what the odds are in terms of getting a lower rating. Okay, so that's the idea here. So it helps us, trying to understand, it actually helps, what's the, real world uses of this. Well, the real world uses could be auctioning, like in Indian Premier League, while the franchise select players. So somebody, the chances or the odds of someone becoming a good player from a given category is what, that's the way they will price different players, and this is one way of doing that. Of course there could be many other factors will play, not just one factor. So the idea here is to understand how it works, and we can include more factors. It's not just categories that matters. In fact, there are other factors like player score, then his his run rate, his strike rate, his average, and so on. So many things um, matter a lot while uh, selecting a player. And that's how it can be done by including more variables, more factors. Finally, we can visualize the probabilities values. So somebody getting a lower rating because of belonging to a given category. Okay, so there are how many categories we have in place? Okay, so how come we have 9 categories? Okay, so this is rating, sorry. So categories are the 4 categories, 1 2 3 4, and 9 ratings, right? In the first category you can see 1 2 3. So which one are the highest, most rating? I think it is 7, uh, 7 8 and 9. So 7 8 and 9 are the are the ratings mostly given to the category 1 players. Okay, and they're good rate, they're getting good rating, right? Similarly, you can see that for category 2 they're getting 5 6 7 8. 5 6 7 8 are the most category. Just look at the colors and compare here, and you will get to know that. Similarly, for category 3, you are mostly getting 4 5 6, yeah, 4 5 6, and for category 4 you are mostly getting 2 3 4 5. Okay, something like that. Okay, so you can see, you can compare the odds by looking at this visual plots, and it's much more clear. Okay, so once you have this model in place, you can also individually score each players and find out the probability of someone belonging to a given uh, rating, or somebody getting a rating, given rating. That also can be done. So we can use a score keyword and get the values. Okay, so that's basically the idea of ordinal logistic regression, wherein we are using multiple category instead of just 2 categories in a normal logistic regression to find out the probability and to find out the odds, or the odd ratio rather. We'll take an example to understand the stepwise logistic regression. I'm going to show you how to build a logistic regression using stepwise variable selection methodology. So we'll take a data set. So here is a data set which is the details of cancer patients, and they have undergone medications, and we need to predict what is the probability that somebody has been uh, completely free of cancer. Okay, and in medical terms we call that as complete remission. So if somebody is completely free of cancer, then we assign a value of 1, otherwise 0. And there are several factors that contribute towards this probability. Okay, so whether somebody is completely free of cancer depends on the 6 variables. Okay, and we'll build a model, a logistic regression model to find out what is the probability that a patient is free of cancer. Okay, so to do so, and you have seen in the data set that the variable of interest has value of 1 and 0. So in such a case, when we have only two values in the target variable, we cannot use a linear regression. We have to use a logistic regression or a probit regression. So we'll go ahead with a logistic regression. Okay, so in SAS we use the procedure logistic, and the syntax is pretty simple. I'll explain it to you. Proc logistic data, and then cancer, which is the name of the data set, and then we're going to get our statistics, model statistics in a data set, and that's where we're saving it as, we're calling it as betas. And then we'll define the model as this model, and the target variable is Remis. We'll write that in the left hand side, and then we put all the factors as the independent variables in the right hand side. Now here Proc logistics by default it considers the lower value as the variable of, or the value of interest, but we are not interested to find out whether somebody has cancer. We rather are interested in knowing whether somebody do not have cancer, or somebody is free of cancer after medication. So we're interested is in predicting 1, not 0. So we have to mention this explicitly. Okay. All right. So this is the basic syntax of logistic regression, and then we'll come to the stepwise. So I'll start with the basic syntax, basic logistic regression. So I'll remove the selection part, and then we'll run this first, and then we'll go over to selection. So this is the plain vanilla form of logistic regression, which has got only the model and no variable selection or no feature selection in place. Okay, so let's run this. So how do we interpret the results? So you can see in the result, the first thing we need to see is that whether it has converged or not. Okay, so we need to see the convergence status first, and here you can see the model convergence status, and you can see that the convergence status or criteria has been satisfied. That means the result that is going to be followed is likely to be correct. Okay, if that's not satisfied, then you cannot explain the results that is going to come out of this estimation process. Okay, so there are few important statistics which are of interest to us. Model fit statistics, which is AIC, archaic information criteria, squash Bayesian criteria. Now these statistics are used to compare models. When you have similar models, a few of models, so the values AIC and SC are compared to see which one is the best model. Okay, and the lesser these values are, the better is the model. Okay, so since this is a single model, we won't get into the details of it, but while comparing we will make use of these values. Okay, and then testing for global null hypothesis. So the global null hypothesis says that whether your independent variables or the features, the 6 features that you have given as the input, are contributing towards finding out the probability of someone completely free of cancer or not. Okay, so global null hypothesis has the importance that if this is not satisfied, there's no point in going down and explaining things, and this seems to be satisfied, because you can see that it is significant enough, so it's satisfied in this case. That means we are good to go with explaining our model results. The next in the result section is the analysis of maximum likelihood estimates. So logistic regression uses maximum likelihood estimation process to get the estimates, the point estimates. Okay, or rather we call that as beta parameters. We have the intercept and the slope, right? So we have got 6 independent variables, and we have also got an intercept. Okay, so there are 7 parameters we have from the estimation process. So all you need to see is how many of these parameters are significant. So how do we check that? Well, we need to look at the p-values. If the p-value is less than 0.05, then we are sure that the variable is significant at 95% confidence. You can say only one value is significant, right? Or not even that. It seems that all the independent value seems to be not significant. Okay, and that's quite strange, right? And it happens because we have, very less number of observation. We have only 27 observation which we have given. So if we find any kind of issue with this data, we might have some strange result. And this looks quite strange because uh, none of the independent variables are significant. Okay, now we'll do an investigation into this. So before that, among the other thing that's important to us is looking at whether so what to what extent um, the model is doing good job. So for that we need to look at what is known as the C statistics, or we call that as concurrence statistics. So C statistics lies between 0 to 1, and it has to be always greater than zero point 0.5. Otherwise there's no point in building a logistic regression model. Okay, so it most of the times is lies between 0.5 to 1, and the closer it is to 1, the better is the model, and we have got a value of 0.88. That doesn't mean much, but we need that value to compare a model. Okay, so we will have several models in place through various techniques, and concurrence statistic is going to be useful while selecting the best model. Okay, so the one that we have seen is the basic form of logistic regression model, and what we have seen here is that there is some issue with this model because none of the independent variables are coming out to be significant. Okay, now oftentimes what happens is that some of the independent variables are not very important. In fact, they cause issues in the model. They cause the good variables. Some of the not so important variable cause the important variables to be not significant. Okay, so they affect the model adversely by making the good variable or the important variable insignificant. Okay, that we need to tackle. So we need to remove this unwanted variable or insignificant variables or not so good variables. So how do we do that? There are several selection techniques available. The popular ones are stepwise selection and forward selection, backward selection, and there is also another thing which is called subset selection, which we're not going to talk about it here, but we'll give a brief idea what subset selection is. Okay, so we'll use the first selection method that we're going to use is stepwise. So the same syntax except the fact that we're using a keyword selection, and then we are using stepwise as the selection method. Okay, so stepwise will remove some of the unwanted or unimportant variables from the model while estimating. So we'll have only the most important variables, and we hope that is going to improve the model. We have a few more syntax. Okay, two important syntax, two important keywords to remember is to have control over which variable is to be included in the model and which variable is to be not included in the model. If you don't use these two keywords and use that as part of your code, it is going to use the default you know um, values. Okay, default entry criteria and stay criteria, But if you want to have control over it, you can point. So what these values are? SL entry. SL entry is like what is should be the cutoff value for which would be used for an independent variable to enter into the model. And once it has entered into the model, um, so what is the criteria to keep it in the model? Okay, so these two are important to select a particular variable whether to be there in the model finally or not. Now why this question comes is because in stepwise regression equation you take stepwise approach. You do not build a logistic regression at once, just like we have done in the first case. We rather will have several such logistic regression with different set of independent variables. We'll see that in the result. So we'll first run this one. Okay, now that we have the result in front of us, so I'll straight away explain how the stepwise selection procedure works. Now, I have already said that there are several steps involved. In the first step, we do not have any variables. So the logic behind stepwise regression is that it is going to start with 0 variables, then it will add the most important variables and see if it is significant, and if it meets the selection criteria. If it meets the selection criteria, it stays, and the next important variable gets added to the equation, and then there is going to be another estimation, and then it will continue till the time we'll have all the important variables are in the model. Okay, now there are few cache. The first thing is that the entry criteria that we have mentioned should be satisfied. Okay, so it starts with step 0. It only has the intercept. So when we have intercept, it's nothing but the mean of the target variable. Okay, then in the next step, okay, the first variable li is now considered to be the most important variable out of the 6 variables. Now it enters the model. Now once it enters the model, because it has satisfied the criteria, it also stays with the model. That's what we have seen, because it is significant, right? It's less than 0.05, and it also meets the criteria for staying in the model. Now this is the criteria to stay in the model. Now internally it calculates the value, and it has found out that the p-value has to be less than 0.35 to stay in the model. Okay, and the p-value has to be less than 0.3 to enter into the model. Now both criteria have been satisfied, and this particular variable stays in the model. Okay, the second step, okay, in the step 2, so the next most important variable will be included. Okay, so which variable has been included now? So we have temp. So the second important variable is temp, which is now part of the model, and it seems to be not so significant, but we'll see whether it actually is the criteria of staying in the model is satisfied or not. It could be satisfied, so internally it evaluates, and there seems to be no effect. That means it doesn't drop out. If it doesn't satisfy that, it will drop out of the model, right? It might drop out, but it seems no effect in the model in steps 2. That means the 2 important variables that we have included so far they stay within the model, and none of them drop out, because the stay criteria has been met. In the third step, the variable cell is now part of the model, and whether it stays or it drops down, okay, it doesn't drop down, so it doesn't drop up from the model, it stays in the model. Okay, and the final message that no effect made for 0.3 significant level for entry into the model. Apart from these 3 important variables that entered and stayed in the model, no other variable, the last 3 variables, did not meet the entry criteria. So a variable which did not meet the entry criteria will not be checked for stay criteria. because it doesn't enter also. Only when the variable enters the model, it will be checked whether it it satisfies the stay criteria. Only if it satisfies the stay criteria, it stays in the model. Otherwise, there's no point in including these variables in the first place. So the message is clear: no additional effect made the point 3 significant level for entry into the model. Alright, so we have finally 3 very important variables. And alright, so now we have the variables and the significance level. We can see one variable is significant, the other two are not so significant, but given that we have small data, we have been slightly um, liberal in terms of keeping the variable at even lower significance level. Okay, so first one is very significant, the other two are not very significant, but they actually help you they help in predicting the target variables. Okay, so have been slightly liberal on that. Okay, and the concordance statistics also is important. So let's see what the concordance statistic is. So the C statistic is 0.889, which is slightly improvement from what we have seen in the plain vanilla, the first model that we built. Okay, so that's about stepwise regression model. Now the good thing that has happened is that, so in a first case there was not even a single variable which was significant. Now we have at least one variable which is clearly significant, and the two variables which are not significant yet they're contributing towards predicting the target value. Okay, now we can also see other selection techniques such as backward selection and forward selection. I'll briefly talk about these two techniques. Okay, so the syntax remains same except the fact that in the selection I have used backward instead of stepwise as we have done in the previous one. Alright, so in backward technique what happens is that you start with all 6 variables and then you keep on dropping till the time your entry criteria or exit criteria is not. So we haven't mentioned any entry or exit criteria, so it is going to take the default one. Okay, so we started with six variables, independent variables, and we'll see in what. Okay, so in the first step, this variable blast is now removed from the, because it doesn't meet the stay criteria here, right? It starts with all variables. In stepwise we started with no variable and then it entered, and it could drop at any time also. In backward it starts with all variables and it slowly drops the unimportant variables. The first step, blast, gets dropped. In the second step, this variable infill got dropped. In the third step, smear got dropped, and finally I think everything else met, and the 0.35 significance level has been used while dropping them. So the stay criteria has not been made for three important variables, unimportant variable, which have been dropped out from model. Now finally you will have your estimates as this, and you can see here also we have one significant variable and two nearly significant variable. Okay, and also need to look at the C statistics, which is same as what we had got in this stepwise regression. So finally we'll see the forward selection criteria. Well, in forward selection criteria, it's exactly the opposite of backward selection criteria. So it starts with no variable, okay, and keeps on adding. But you might wonder, how is it different from stepwise, because stepwise also does the same. Well, in forward selection, if a variable is is part of the model, or it has been entered into the model, it will never drop off. Whereas in stepwise, it can drop off at any step. Okay, so if a variable x has entered into the model, it can, in the first step, in the second step, it might drop off, because in the presence of second variable, it might not be significant, it might drop off. But in forward, once something is part of model, it is never going to drop off from the model. It is going to be there in the final model as well. So in the three steps, I think here also there are three steps, and in each step, the most important variable in the order of importance gets added to the model, and I'm sure 0.3 significance level has been used to, so um, in backward, we have only the stay criteria, the significance level for stay criteria. In forward, we have significance level for entry criteria. In stepwise, you have significance level both for entry as well as for stay. So stepwise is a combination of, it combines the forward and backward, and that's why it's considered better than both these two selection techniques. And as we can see, the result is more or less same, except the fact that there is slight, I rather say it's same. So so in such a case, when we have only 6 variables and 30 observation, there won't be much of a change. But if you have large set of observation, and if you see a large set of variables and you use these selection techniques, you will see a significant difference in terms of finding the most significant variables, or the best set of variables, and um, also in the concordance statistics, which is going to give you an idea of how efficient your model is. And how do we select? Yes, so the important is, given the fact that we have now many selection techniques, which selection technique is to be finally used? Well, the one that is to be used should have the highest predictive ability, and that would be that you can find out by looking at the C statistics. The one that has the highest C statistics, go ahead with that. And if you have similar C statistics, look at the AIC and SC values. AIC and SC, right? That's what we have shown in this case. If you go on the top, you have AIC and SC, right? So okay, somewhere down you have AIC. Okay, here. So look at the AIC values and compare. The one that has the lowest is the one. So start with C statistics, compare. The one that has highest should be taken, and there is no question. If they're all same, then go to the AIC and SC criterion, and the one that has the lowest AIC should be used as the final model. Now finally, given the fact that stepwise regression does a good job, um, we'll go ahead with stepwise. And what we have done here is that we are also predicting a value, or technically we are calling that as scoring a value. So we have a model which has got three significant or three important variables in the model. So using the statistics, the beta parameters, we will score the model. So what do we get in the score? We get the probability of someone having cancer or not, right? So that's the main output we are interested in, and that we'll have in the data set PRED. Okay, so here, against each individual patient, you have a probability value which lies between 0 and 1 of somebody completely free of cancer or not. The first candidate 0.72. So it's saying that it's likely that the candidate is free of cancer, and the actual value is 1, so that matches. That's a correct prediction. Second, it's 0.57, and it's also 1. So cutoff value that we normally take is 0.5. That means anything above 0.5 probability is considered that it is giving a value of 1. So the actual value is 1 and the predicted value is 1. So it's a correct prediction. So you look at these values and see how many times you have got correct prediction. Okay, that will give you confidence before you can use this model in the production. That means you can use this model um, to score new patients, to know whether someone is completely free of cancer or not. There's also a lower limit, confidence limit, and higher confidence limit for each one of these predicted values, so that it gives you an idea, what is the bracket, or what is the lower limit and upper limit of this probability value. But what's most important is this one. Okay, so we have been able to score this. Now this can well be used for new data also. Like for this data we already have the target variable, but for the new data we may not have the target variables. So by looking at this probability values and taking 0.5 as the cutoff, we can find out whether somebody is free of cancer or not. So that's a small example to understand the stepwise logistic regression, and how stepwise logistic regression is different from forward logistic regression and backward logistic regression. Thank you.
In this video, I'm going to discuss about how to build a customer churn model or a churn prediction model. So in this video, we're going to learn how to build a regression based model which will predict the churn. And for this, I'm going to take a dataset from a telecom industry, because this is primarily seen in telecom industry, that customer tend to go to the competitors very often. So how best we can predict the churn, so that necessary measures can be taken. So the objective of the study or the model is predicting probability of churn, that customer is going to leave the company, is going to go to the competitor. So what is the probability of that happening? Okay, so I'll take a data set. Let me show you the data set. So this is a data set. I've got the customer ID, the retain indicator. If a customer has left the company, or left the the company is no the customer is no more with the company, the customer is no more a customer of the company, then the retained indicator is 1. Or if it's still with the company, then the retained indicator is 0. Or if the churn has happened, it's 1. If it hasn't happened, then it's 0. I have got gender. So a sex indicator, 0 is male, 1 is female. Income status, I've got two types of people. So people with higher income status and lower income status. So 1 is higher income status and 0 is lower income status. Marital status, 1 is married and the 0 is unmarried. So so in total I have got 4 variables. So my dependent variable is going to be retain indicator, right? Because I want to find out the probability that a customer is going to churn or not. So that is going to be my dependent variable. Sex indicator, income status and marital status are the independent variables. So I've got 3 independent variables here, and all 3 are categorical type. I do not have a continuous variable here. So I've got 1 dependent and 3 independent variable, and using these 4 variables I'm going to build this model. Okay, so the first thing to see is that what is the percentage of people in our sample, the one we have taken, have actually churned. So we take a proc frequency of the data with respect to retained indicator. So 38% of the customer have actually churned in our sample data set. So that's a good percentage, and this high percentage is actually seen in telecom industry. So and why are we checking that? Because what happens is that if sometimes the
event of interest. So event of interest here is churn is too low. For example, 3%, 4%. That's like too low. You can. It's difficult to build a model with that kind of a churn. So we need to take necessary measures for that. We need to do a lot of things with the sample in order for the sample to be good enough for the study. But we do not have a case like that. So 38% of event is actually is a good percentage. So the event to non-event percentage is ratio is 38% to 61%, as you can see here. So we are good to go. Yeah, like any when we build any model, we do the data cleaning, variable selection, and data exploration first before we build the actual model. So we need to remove the variables with too many missing values, and if a variable has acceptable number of missing values, then we need to do the treatment. But in our dataset, we do not have any missing variable as such, or we do not have variable having a significant number of missing values. So the next step is to remove variables with only constant values. So these variables do not explain anything about the dependent variables. So variables where the values are all constants should also be removed from the dataset. We also need to see the correlation matrix. So if the variables are continuous in variable nature, then we need to see the correlation matrix to find out that if a certain number of variables are duplicates, or there is high correlation between independent variables or not. So if there is high correlation between independent variables, then we need to take necessary measures. We need to remove one of the correlated variable from the dataset. We should also need to ensure that the correlation between the dependent and the independent variables should be significant, whereas the correlation between the independent variables should be as minimum as possible. So that's important. So in our data set, actually we have only categorical variables. So the Pearson correlation is not going to work. We should actually use the polychoric correlation in order to find out the correlation in this case. And we may need to also use transformation, different type of variable transformation in order to find out the variable strength. So we may need to use the WA transformation and find out the information values. WA transformation helps treating the outliers, treating the missing values very effectively and efficiently. And information value help us find out the variable strength. So variables with high strength should only be used for the model. Variables with minimum predictive strength should be totally ignored. And then dealing with the extreme observations, if you're not using WA transformation, we need to take care of the extreme observation very effectively, ensuring that it doesn't affect us. But in our data set, we do not have a continuous variable, so there is hardly any extreme observation, and we in fact we do not have any extreme observations. Then we also may need to do transform variables. We may need to do a lot of variable transformation. For example, we may need to take logarithm of the independent variables or exponential of the independent variables. Why do we do that? Because sometimes the actual variable do not have a relationship with the dependent variable, whereas the transform variables have got relations. It has got some relationship. So we can try out all these things. So after doing all these things, we can directly move on to some more exploration. So like in any predictive model building, we start with Proc means. We check the descriptive statistics. We look at the frequency counts. We so we do a lot of plots to find out the pattern. It actually helps us understanding the data better. So we should do the means, frequency, and different charts. So I'll ignore this part because this part is pretty trivial and it is pretty similar in almost all model building. So I'll not cover that in detail. So the next thing is to find out the segmentation. So when you build a model, you need to know whether one model is going to be sufficient for your data set, or you need to have multiple models. Well, why do we need to think about that? Because sometimes what happens is that one model will not be
will not fit your data properly. So we may need to have different models for different category of data. For example, if say for example we have got telecom data for two different markets, Indian market and American markets. So the customer behavior in India and customer behavior in US are, you know, could be different. So we can have two different models instead of one model. So or sometimes the behavior of male customers could be different than behavior of female customers. So we may need to have two different models for different genders. So what do we call it as is we call it as segmentation. So we need to take a segmentation decision. There are better way of doing it also. We can use cluster analysis. We can also use shade or cart algorithm in order to do the segmentation decision. But I'll take a very simple a simple way of how we can do it very simple in a very simple way. So I'll take a frequency. So one of the way we can do segmentation is based on the gender. Now let me see whether we should actually do it or not. So what we do is that we just take a frequency count of the repeat indicator or the event non-event indicator, which is the return underscore I, which is our dependent variable. We should take a frequency count with respect to male and female. So let us take it. Okay, now we can see that the okay, so this is my output, and as I can see, the repeat indicator in the case of male is 23%, and in the case of female it's 21%. If I'm not wrong, yeah, it's 23% and 21%. So the difference between the event and non-event percentage, with respect to the to different genders is very minimum, or it's within an acceptable range. So we probably may not have two different models. Instead, we can have a model which will cater to the both the population or both the genders. So if had we have a difference, a pretty large difference in the percentage of ones with respect to zero, then we could have say two different models. For example, like 15% and then 25%. So that's a gap of 10%, right? So there we can actually have two different models. But here we can go ahead with single model. The next thing to do is to do a sampling. We probably would have taken already a sample, but the sample has to be divided into two types. One is training sample and it's testing sample or validation sample. So why do we do that? We build a model on training sample and we test the model on validation sample. So what is the reason we do that? Well, the model that we are building here may not work in a new data, and our intention is to build a model that is going to work in the new data, because the data that we have with us is historical in nature, and we are least bothered about what is happening with the historical data. But the assumption here is that the history is going to be repeated in future, but that doesn't happen all the time. Sometimes we fail to capture the pattern in the historical data, and how much of it is going to be continued in future. So to test the model, we build the model in a training data set. So we take a portion of the sample data and build the model, and we test the same model in another portion of the data. That is, the second portion is considered to be a new data set, and we see if the model statistics are consistent or not. If that's not, then we need to improve the model. So we use Proc survey select for this, and we will use the simple random sampling, and I'll take 60% of the data from my sample for the training. So I use the methodical to SRC, and sample rate is 0.6. That means I am taking 60% of the data from my master data, which is telecom, and I am saving it in a different dataset name. The name is training. Okay. Now training is the data training dataset that I am creating. Okay. Now 60% of the data from telecom is training, so rest 60%, 40% has to be in the validation data, right? So what I'm doing is that I'm just merging back the training data set. I'm just merging back the training data set with the master data set in order to find the validation data set. So I'm just taking the observations which are not there in training data set and there in telecom data set. We can do it using SQL statement. I'm doing it using merge statement here. So I'm using take A and not B. That means observations which are there in telecom but not in training. So those observations are going to be in validation. We can do even more number of validation. We can take random samples. So just by changing the seed value, we can take random samples and have as many number of validation sample as possible. But generally, having one validation sample is very important, and that's validation. Okay, I have taken two more validation sample, validation 1 and validation 2, by changing the seed here, as you can see. Now, when the sample, we will run the sampling first. Yeah, we will get the sample data first. Okay. Now you can see in the result that your sample data set is created. For a check, you can actually do that whether in your training and validation data set, the percentage of ones or the percentage of churns is actually consistent or not. So do a proc frequency data training table written indicator. Right, so that's also 38%. So the main data set had 31% of one, and here also it's 38%. So it's consistent. So let us check that for validation. I assume that it should also be fine because it comes from the same subset. Well, yeah, it's 41%, little on a higher side, but should not be an issue. 39% and 41%. So the difference of 2% should not be an issue. Then we start building the very simple model. So when we build model, we actually should try with a very simple form of model without using any variable selection criteria. Just put all the independent variables in the model and do the regression. So since you know that the dependent variable is a binary variable here, I have got only ones and zero. I cannot use some multiple regression. I have to use a classification technique. So the classification technique that I am going to use here is the logistic regression classification technique. We can use other type of classification technique as well, like discriminant analysis, but I am going to use logistic regression over here. And logistic regression also gives us the probability. So that's another important thing why we use logistic regression, which is a powerful technique. So proc logistic data telecom, and then in the model statement, in the left hand side of the equal to sign, I have the dependent variable, and in the right hand side I've got three independent variables. So let me run this. Some issue. Okay. Okay, let me show you the output here. You can see that the estimates are all significant. All three estimates of the three independent variables, including the intercept, are all significant. Okay, and the concordance is 67%. The concordance has to be greater than 0.5. It's one of the important criteria. So it is greater than 0.5. So that's one thing to note here. And the variables are all significant. So that's one good thing. But the question arises that can we improve the concordance? Can we better the model? Model with a higher predictive power. Of course, we can try. We can try with more variable transformation and variable reduction technique, and so on, and see if we can improve the concordance of the model. Now let us use the variable selection criteria. So the variable selection criteria available for Proc Logistic are Stepwise selection, forward, backward, subset selection. I'll just use one variable selection, stepwise selection, and probably when you try, you can try with forward, backward, subset selection, and see which selection criteria is actually giving us highest C statistics or highest concordance statistics. So I'll use the stepwise selection criteria, and I'm going to save the model this time. So I'm going to save the model in a data set known as outreg. So the predicted values of the predicted probabilities are going to be saved in the data set. I'm also going to save the model statistic using the keyword out model. So using out model, I'm going to save the model statistics. And why am I doing that? Because I'm going to use this statistic to score the new data set. That is most important, or to validate the data set, new data set, right? So let me run this. And yeah, we need to use descending. Last time we did not use. In fact, we should have descending over here. Descending because we are modeling for 1, right? We are modeling for the event. Event is 1. Retail indicator equal to 1. If you do not use descending here, Proc Logistic by default model for 0, and we are not interested in that. We are interested in modeling for the 1, or the probability that return indicator takes the value of 1. So let us run this. So we can see that the estimates are again significant, and the concordance statistics is very same. There is hardly any change in the concordance statistic. That's the reason why the C statistic is not different when we use selection criteria here is because we do not have too many independent variables. If you have like too many independent variables, say for example we would have started with 30, 40 or 50 independent variables, then the C statistics would have changed and most probably would have improved, and the total number of significant independent variables would have reduced. But since we have only 3 independent variables here, so we can see that there is hardly any change. Okay. Now once the model is built, we have the model in place, we have the model statistics in place. So what is so important for us is to have the estimates. And so estimates are important because we can use this estimate to score the new data set, right? So and we have saved our data set, the model statistics, in the out mode data. If I can go and show you, I have the data set in the model statistic in the out mode data. So this is how the test statistic look like. This data set is going to be used for scoring purpose. So this is an important data. We need to save it carefully. And the same data set, the one we have used for model building, is there also we have saved the probabilities value. So the name of the data set is outreg, and you can see in the same data set we have the estimated probability, right? So estimated probability says that the probability that a customer is going to churn. For example, when you see the first observation, the probability that the customer with customer ID 1 is going to churn is 0.2. Similarly, for the customer 2, it's 0.4, 0.47 for customer 3. So that's the way it is. We have made one mistake here. We should have used training dataset instead of telecom dataset, because we should build the model on the training dataset. So we will run it again. Okay, fine. Now once the model is built, we have the model statistic in place. We need to score the validation dataset to see if the model statistics are consistent in validation dataset or not. So let us score the dataset. So how do we do that? Proc logistic in model, see the keyword. Now in the proc logistic, in the previous time we had out model. Now we use the in model here, and we use the out model where dataset where the model statistics are saved, and then we use the keyword score data, and then use the input dataset, which is validation, the one that we have created when we did sampling. And once this this dataset is scored, we are saving it in a different name, validation underscore, right? So now let us run this. Let us take the log, and it scored successfully. Now it is scored. We need to see if the concordance, the C statistics in this case, is similar to what we have seen in the training dataset. Otherwise, then there is an issue. The model is not working fine in the new dataset. It is working fine in the training dataset or in the historical dataset, but in the new dataset it may not work fine. So we need to see that. So how do we find the C statistics? In this case, we need to use proc frequency data, and then we have saved the dataset, the score dataset in validation underscore score. So let us go and see that dataset, validation underscore score. So there we'll have the probability values as well. Probability of return indicator is equal to 1, and probability of the return indicator is 0. So we have the probabilities values. Once we have the probability values, we can actually calculate the concordance or the C statistic by looking at the probabilities values. So proc freq data, validation data underscore score, table return indicator, and p underscore 1. So what is p underscore 1 here? Well, p underscore 1 is nothing but the column name, probability return indicator is equal to 1. So this is how it is. So name of this column is p underscore is equal to 1. And we compute different measures. We compute so many different measures, and one of the measures that we are interested in is Somos-D statistics. So the above syntax gives us some Somos-D statistics, and using Somos-D statistic we can calculate the C statistics. So let us run this. Now you can see the Somos-D statistic is 0.3 in this case, 0.3057, the one I have highlighted here, 0.307. Now using Somos-D statistic we can compute the concordance or C test. You can see I am highlighting you here. C statistic is 1 plus Somos-D whole divided by 2, and Somos-D statistic is 0.3. So the C statistic is coming out to be 0.65. So the concordance or the C stat value in the training data set is 0.669, and here it is 0.65. So they are very close. Should be even more closer ideally, but still it's in an acceptable range. So we conclude here that the model is not only working fine in the training dataset, it's also working fine in the validation dataset. Hence we are sure that it's also going to work in the new data that is going to come later on, or the dataset that is we are going to get, and the model is going to work fine for any dataset that we are going to get. We may need to do more validation actually by taking so many randomly taken samples from the master dataset and see if it is working fine or not. We can also create simulated data and see if the model is working fine or not. Even after being very sure that the model is working fine in the validation dataset, we actually do model monitoring every month or every quarter or even every week. So that point of time also we see if the model is working fine. So if it is not working fine, then one need to rebuild the model or re-estimate the model again. So even after the model is built, we also do this validation later on. Once the model is validated, we assure that this model is going to work fine. So this is final model with us. Okay. Now the important thing is that having a model is not a final thing. We need to think about that how we can use this model for you know, finding out that how many customers are going to churn in next few days or next few weeks or next few months. So how are you going to predict that? Okay, what cutoff value should we take? So these are some of the questions that one should ask before implementing this model. Now, what is the output with us? Well, the output that is with us is the probability that a customer is going to churn. Say for example, the probability is 0.3. So if the probability is 0.3, is this customer going to churn? We do not know. So what cutoff probability should be taken as a threshold cutoff is very important. Now, a lot of times 0.5 is taken. Theoretically, 0.5 is the sound. I mean, by default, most of the times 0.5 is taken, but that's not ideal all the time. We may have to change it or adjust it a bit. So let us first take the 0.5 and see the problems or the issue that we are facing and how we can actually better it. Once we have the predicted probability, it's good to have the descriptive statistic of the probability column, probability variables, so that we will get to know what is the mean probability and what is the maximum and all that. So the mean probability is 0.38. The maximum is okay, we do not have a maximum, so we can actually take, yeah, we have a maximum. So the maximum is 0.62 and the minimum is 0.2. So the minimum probability of churn is 0.2 and maximum probability of churn is 0.62. And we have got the quantile distribution of C. So we can see how the probability of churn across the population is being distributed. Okay, so this is how it looks. Okay. Now let us see how many of these customers are having a probability of churn greater than 0.5. We can do that using Proc means. Now you can see that 654 number of customers are having probability of churn greater than 0.5. So out of this 3500 odd sample or observation, 650 number of customers are going to churn. That's what it says. That's what the predicted probability says, right? But okay, so let us assume here that okay, this is the cutoff value. Okay, so at this cutoff value, we already have customers who have already churn. So the actual data is with us. We need to see the predicted data. Now using the predicted probability, we can categorize customers as retained customer or churn customers. Okay, so that will be predicted variable. We already have the actual variable and we can do a comparison, right? So what we do is that we just take a cutoff value 0.5. So people with greater than 0.5, predicted values greater than 0.5, we categorize them as retained indicator underscore predicted equal to 1. That means the customer had churn or is going to churn, and rest customers are categorized as 0. Now let us run this. Let us go to the outtake data. So now we have the actual data. So this is the actual retained indicator and this one is the predicted retained indicator. Now we need to see what is the accuracy level, right? Or like how many zeros are zeros and how many ones are 1, right? For example, you can see in the first customer, the actual retained indicator is 1, whereas the predicted retained indicator is 0. So that's the mismatch. So we just need to know how many these are mismatches, how many these are matches, just to see if the model is working fine or not. So we call it as confusion matrix. So that's that's one technical jargon used here. So we can do a proc frequency with respect to the actual predictive return indicator and the predicted return indicator. So let us run this. Okay, now what we are interested in is that the first matrix and the last matrix, the fourth quadrant, or the first quadrant and the last quadrant, right? Zeros categorized as zeros. So 85% of, not 85, okay, 1650 observations are categorized as zeros, and 378 observations ones are categorized as ones. Actual churn customers have been categorized as predicted churn customer, and similarly, non-events categorized at non-events. So the first quadrant says zeros categorized as zero, and the fourth quadrant says one categorized as one. The second and third quadrant are the mismatches, and we can see 822 mismatches in the case of 0 categorized as 1 and 276 mismatches, ones categorized as zeros, right? So there is a fairly good number of mismatches happening here, right? So why is it happening? So can we better it? Of course we can better it by taking a better cutoff value. So the default cutoff value 0.5 may not work well all the time. So we need to find out what is the cutoff value that actually suits the organizations. Sometimes organization would have its own policies, may not be directly from the data, but they may be having their own way of finding out the cutoff values. But one of the way, and it's pretty crude way also, there is no statistical theory as such to justify this, but yeah, that's one of the way people get to this. So let us first okay, so we have got 3500 observations. So let us keep it a limit. Let us work with only 3500 observations. So I'm just substanding the data for the simplicity purpose. I mean, we can go ahead with the entire data. Okay, so we have 3126 observations. So let us take 3000 observations. Okay, I'm just ignoring a couple of hundred observations to make our life easy. This is for validation purpose, so that should not be an issue. Okay, so outreg now has 3000 observations. Okay, now what I'll do is that I'll classify the 3000 customer into 10 different groups. Okay, and I'll tell you why I'm doing that. I'll classify the customer into 10 different groups, and the purpose of doing this and what I'm going to do from here is to find out, first thing is finding out a proper cutoff value. The second thing is validating the model, stricter way of validating the model, and also understanding your model in a better, right? So that's the purpose of doing all these things. So let's explain you what are things that we're going to do from here. So a couple of steps to be done. First, we need to create a simple data set, a test data set, wherein we just have data points for, we just have 10 beans. Okay, so 3000 observations, 10 beans, each bean having 300 observations. Okay, so I'm just keeping a data set I, and I'll show you what data set I'm creating. So this is like a grid. Okay, you'll be able to understand when you see the actual output. Let me go to the test data. So this is the test data that I have created. So I text 1 to 10, and each value gets repeated 300 times, right? So total number of observation here is 3000, right? Then what I'll do is that I'll sort my predicted value, the data set where my predicted values are there with respect to the predicted probability, right? And I'm going to sort it in ascending or descending order. So let me sort it. So let us go and check how outreg look like now. Yes, now this is sorted in ascending order, right? You can see the observations here in the ascending order, right? Starting from 0.2 till 0.62, right? Now what I'll do is that we have created a grid data, right? the data set name is test. I'm going to merge this data with this data so that this entire data is going to be divided into 10 different groups in an ascending order. So the first group is going to have the least probabilities values, and the next group will have little more probabilities value, and so on. And the last group is going to have the highest probability of churn. So why I'm going to do that? Well, the intention here is to find out the number of the percentage of churns happening in different deciles. So what do you mean by decile? Decile is nothing but just 1/10 of the data. So how at every decile I'm going to have the percentage of churn? Okay, so let's merge back and it will be more clear when I see the data set. So let us merge back the data and we'll have the indicator I in outreg now. So let us go and see. Now we have the indicator with us. And you can see I equal to 1 and estimated probability is 0.23, 0.2, something like that, right? So it's the least probability. If you go to I equal to 2, then the probability value will increase. So that's another decile. I equal to 3, third decile. I equal to 4, fourth decile. So with respect to decile, the probabilities values are changing or it's increasing. It's monotonically increasing, right? It's in increasing order. So we just find out that what is the percentage of actual retained percentage or actual churn percentage with respect to these different deciles, right? That's what we are going to do. Once we have this data set in place, we are going to summarize this data set. So how are we going to summarize? We're going to summarize, we have this 10 beans or 10 deciles, and then we want to take this take the count of the retained indicator equal to 1. So how many customers are churning or how many churn customers are there in each bean? So that's what I'm calling it as churn, and I'm going to do it with respect to the different beans or the different deciles, right? So I just write a SQL code for that and let me run this. Right, so let me go to the summary. This is what it is. Now the first bean, okay, now remember what the beans mean, what is significance of these beans. The first bean means the predicted probability is much less, and it increases with increase in the decile or the bean, right, value. So in the first decile I'm having only 49 churns, second 55, 65, and then it's increasing. So the maximum churns are happening when it is 176, right? Sorry, in the 10th decile. The maximum number of churns 176 is happening in the 10th decile, right? So I need to find out the percentage of churn happening in each decile, right? So let me take this data to an Excel sheet. I've already done that. You can actually take it directly from here, from SAS work datasets. So this is how I've actually scored the full data or the entire data. So not just a trainee dataset, the entire dataset, right? So that's also fine. That's not an issue. Now you can see that the churn percentage, right? And I have done a little bit of adjustment. So I've just kept it in a descending order. So I just I've just changed it the order instead of decreasing order. I've just increasing order. I've just created a decreasing order. Okay, so the first is like 50%, 15% of churn, then 13% of churn, and it's going down. So it's just a reverse of that or a transpose of that, right? Okay. So what are the things I have done here? So initially I have got these two values from the SAS dataset that I have just shown here. I have the bean and the corresponding number of churns. So don't be confused. The dataset where I have shown you the number of churns, the first bean has least number of churns, but here the first bean has maximum number of churns. Just that I have changed the change the bean values here just to make it more easy to understand. Okay, it doesn't actually change the objective of the study. Once we have the actual churn, you just take the total count of that and find out for each bean what is the percentage of churn happening, right? So that is the percentage of churn. For the first bean, 15% is happening. For the second, 13%, and it is going down with increasing bean, right? and also find out the cumulative, right? And imagine a situation, if you just toss a coin and pick a customer, if he is going to be churning or not, if a customer is going to be a churn customer or not, it is always going to be 50%, right? It is always going to be 50% chances that a particular customer is going to churn if you do not use any predictive model. It's purely random. So if you do it at a random, the entire distribution is going to be distributed uniformly, right? So each decile will have 10% of churn. But here you can see a non-uniform distribution starting from 15% till 4%, right? So we have a random distribution and we have a distribution which is found by the predictive model, right? And we can also have a cumulative random distribution as well. Now we do a plot. The first plot, which is the percentage of churn, is a plot between the bean, the first column, the column A, the column C, percentage of churn happening, and the random distribution or the random percentage of churn if you do not use any model. Now this is the highlighted one is the chart. Look at the left chart here. Now you can see that for the first bean, the predictive model is performing much better than the random distribution, right? Similarly, in the case of, one second, I'll just delete this. Okay, it looks better. Similarly, for second bean also, the predictive model is actually doing much better. In the third decile also, the predictive model is doing much better, and it's leveling at decile 6, right? So till decile 6, my model is outperforming a random guess, right? And that's the objective of any predictive model building, that you should outperform the random guess or the common sense way of finding out or classifying customers, right? So till 6th decile, the model is working very well. The ability of the model to find out percentage of churns is actually outperforming the random. So that should be the cutoff. So the 6th percentile probability value should be ideally be the cutoff, or something close to that should be the cutoff. Okay, and we need to go back and see in our data set what is the probability value corresponding to this this particular bean or this particular decile. Okay, now another important statistic to check here is the cumulative statistic or the cumulative churn percentage. Now this is for validation purposes. Now you take the cumulative distribution and plot it with respect to the cumulative distribution of the random distribution, the one I have explained over here, and this will be done with respect to the means. Now you can see by 6th decile, the one that we have just chosen as a cutoff value, you just take a straight line of that and you are finding it something like 75%. That means you are able to find out 75% of the churn if you put the value, the probability value corresponding to the 6th decile as the cutoff value. I repeat, if you take probability value corresponding to the decile 6, you will be able to predict 75% of the churn, 75% of the churn accurately. So that's a good number. If you do it at a random, it should not be greater than 50%, right? But you are able to do it 75% of the times correctly. And that's the beauty of the predictive model. So that says that your model is working fine. But you can do even more rigorous study on this. So can you build different models using different techniques? For example, logistic regression is not just one classification technique. We can have probability model using many other techniques, many other machine learning techniques and all. And we can look at this graph. So we just have one chart like this for each one of these model, and then do a comparison and see that which one of this is actually giving maximum number of churns. Okay, so this value, when you put your cursor here, you're getting 75% here, right? And the 6th decile, you're getting 75%, right? So at 6th decile, which model is actually giving us the maximum percentage of churn. So that should be the model of final model, or the model should that model should be implemented, right? Of course, it depends on many other factors like the ease of implementation and so many other things. Yeah. So that's the way we built a churn model using logistic regression in SAS. So the important thing here is to know that we should actually do the cutoff value. So to do that, we should actually go to the main dataset, outrage dataset, where we have the predicted probabilities, and let us go to the bean where I is equal to 6. This is the 6th decile, right? And I can see that the estimated probability is somewhere close to 4.43, 0.4, right? So we can just round it off. That could be one of the way, or we can take the average value of the probabilities for this particular decile. That could be another way, or just take the minimum or maximum value of this. So depending on what is convenient, we can just take any of these values and use that as a cutoff value. And once you have this cutoff value, we should go and see how the confusion matrix look. Is it doing better or not? And so that's one thing also we can check. So once we have these probability values in place, we can use this cutoff value to find out if a customer is going to churn or not. So the final thing should be strategy making. If a customer is having probability of churn greater than 0.43, we should try to contact him or try to provide him more offers in order to retain the customers, right? So that should be the strategy of the team. So yeah, so that's how we built a churn model using logistic regression in SAS. You can do the same thing in any other statistical software like R or SPSS or other packages like Python. Thank you.
Hi, in this video I'm going to talk about how to build a time series ARIMA model using SAS. So we're going to take a dataset called AIR dataset. It is there in SAS help. If you go to SAS help, you will get this data. So this data is about the number of international airline travels per month. So that's there for 12 years. So we've got 144 observations. So I'm going to show you the data. So I've already taken the data in my work library, but if you go to the SAS help, you will see that there the data set there. Okay, so we've got two variables. One is the date variable, which is in month, and then the variable of interest, which is the time series variable, is the variable called air. So air is the name of the variable and is also the name of the data set, by the way, so don't get confused. Okay, all right, so we're going to use this data set uh, to build a time series ARIMA model, and we'll do the forecasting. Okay, the first thing that we're going to do is to plot this data set. Okay, how does it look like? Okay, so the first thing to do in any time series model building is to see how the data looks like. So we're going to plot this data. We simply have a scatter plot, and this is how it looks like. Okay, we've got international airline travels in the y-axis and jet in the x-axis, and this is how it looks like, right? You can form some opinion about it, whether it's a stationary data, whether it's non-stationary data, whether there's seasonality or there's no seasonality. All those things just by looking at the plot. But just to keep it simple, I'm not going to form any opinion at this moment, but we'll see these things as we go ahead with building this model. All right. So the next thing we'll see is to get all the descriptive statistics about this data. And how do we get it? We use the procedure Proc called Proc ARIMA, and we'll use this data set, data air, and the keyword that we're going to use is identify, and the time series variable is the variable called air, and then we'll use an option called n lag equal to 24. Well, n lag is equal to 24 is nothing but that we want to see how the data behaves for its 24th lag. Okay, So you can have 36 lakh, 48 lakhs, and so on. So it's an option given to you. You can, usually you get it for 12, for 24, or 36, and so on. Is only for, there's no model building happening here. So you have that option or the luxury of changing things, and getting different kinds of descriptive statistics from this data. So you don't have to worry about what exactly should be the n lag at this moment. So don't worry about that. And let's run this. So this is purely an exploratory data analysis at this moment. So we have this option of uh, you know keep trying different n lags. Alright, so you get the mean, the standard deviation, the number of observations, the different lags, and the correlations, the autocorrelation rather. Why we call it autocorrelation? Because the correlation of the series with its own lag. That's why it's called autocorrelation, right? Auto means self, correlations means self, correlation in it with itself. Alright, okay. So you see there is correlation. Of course there is correlation, because all these things are significant. As you see, the p-values are less than 0.05, so there is correlation, right? Autocorrelation, which is a good thing, because we want our present value in the time series to be correlated, or to be related to its past value, and that's the reason why we are going to use ARIMA model for forecasting. If that's not there, then there's no point building a time series model. It's purely random, and it's not going to help you forecast your future values correctly. Okay, so at this point in time, let me tell you that if you're not familiar with time series theory, please go back and watch my video on time series theory on my channel. There is a 1 hour video on time series theory. Please go ahead and watch that video. You can go to the playlist and watch the time series theory video on that playlist, and you'll be familiar with the basics of time series modeling. And then you can watch this video to see how you can build it using SAS. There are other trend and uh, correlation plots. Yeah, we'll see these plots: the autocorrelation function, the partial autocorrelation function, the inverse autocorrelation functions, and so on. Okay, all right. So what do we get out of this autocorrelation function and partial autocorrelation function? Well, one thing that we are very sure of is that this data is not stationary. Even from the plot, we could see that it doesn't seem to be a stationary series. For stationary series, the mean and the variance should ideally be constant. Okay, and it doesn't seem to be the case, right? Also, if you look at the PA to the autocorrelation function graph, the ACF, there should be a sudden drop in a stationary series, but that's not the case here. You see the drop in the ACF value is is not steep. It's rather quite flat, and that's not the nature of a stationary series. So it's clearly a non-stationary series. Okay, and PACF, we use it for identification of the number of number or the order of the ARIMA series, ARIMA model. Okay, and we'll discuss about that. IACF we never quite use. We very seldom we use, so we don't really look into IACF. Using SCF and PACF, you can very well build an ARIMA model without looking into the IACF. Okay, so the two things that we are uh, very interested to know is whether the series is stationary and whether it is a white noise. So white noise series is basically a random series. So you do not build a time series model on a white noise time series data. So if the data is white noise, you simply leave it there. You cannot build a time series model because it's purely random. There is no point building a model. Well, you can actually see whether there is the data is white noise by looking at the autocorrelation check for white noise. Okay, and you see that the p-values are all significant. That means it's not purely random. There is highly uh, highly high correlation between the lags. Okay, and it's not purely random. Hence, series is not white noise and it is non-stationary. So these two things are clear at this moment. The next thing that we'll do is to convert this stationary time series to an the non-stationary time series to a stationary time series. And how do we do that? We do differencing. So differencing is just about subtracting the lag from its value. So this first order differencing, the second order differencing, we start with first order differencing and we see then whether the time series is now stationary or not. Okay, if it is not stationary, then we go ahead with second order, and then if it is still not stationary, then we go ahead with third order stationary. But most of the times you will get a non-stationary series to be stationary in just first two differencing, so you don't have to go to for third differencing and so on. But yeah, but you still can try. If you are familiar with time series theory, you might be wondering why aren't we doing the statistical test for stationarity checks. Like you can do Dickey-Fuller test, augmented Dickey-Fuller test as well, ADF test as well, right? So you can try that as well. So I'm not going to use ADF for stationarity check, but you certainly can do that. Okay, but you also can look at the series and also look at the ACF value and get to know whether it's a stationary series or a non-stationary series. So we're going to do the first order differencing. How do we do that? So identify var and then the variable that is of interest to us, in bracket just put 1, and that's how we do the first order differencing. And when we do second order, simply change it to 2, and then it's going to be second order differencing. So let's first do the first order differencing, and we'll see whether we get the non-stationary series as stationary series in the first order itself. So what we're going to look at is the ACF. Well, now you see there is a steep decrease, or there is a sudden decrease in the ACF values, right? It's not flat anymore. So it seems that with a first order differencing, we get stationary series instead of a non-stationary one, right? So so we're fine with first order, but we also can look at the second order just to be sure whether the second order is better than the first order or not. Okay, but if both are stationary, then we'll go ahead with first order. Okay, because having less terms is always better, right? Well, you see, this is not better than the first order, so we'll go ahead with the first order, right? Alright, so that's done. The next step is the estimation and the diagnostic checks. Okay, so there are three steps in time series model building. First one is identification, the second one is the estimation and diagnostic check, and the third one is the forecasting, right? So these are the three steps in a box Jenkins method of time series forecasting, right? So the syntax for estimation is very simple. Is use just estimate and then provide what model you're going to estimate, right? So that's something that you need to put in, right? So whether we go to AR1 or MA1, ARMA1, ARIMA 111 and so on, right? Sorry, one ARMA 11. So how do we know which model is to be used? Okay, so let's look at the plots again. Okay, so let's use the first order differencing, and then okay. Now the thing is, there is a strong correlation between the lags. So one thing that we are very clear, right? That means its own lag. That means if yt is the time series, it has high correlation with yt minus 1. So clearly there is a AR term, right? Whether we're going to have a MA term is not, whether that's going to make the model better, we'll see later. So we can try several models to see whether we can use MA term as well in combination with AR terms. Okay, but now we have already done the differencing. Okay, so there is already the I term. In ARIMA we have AR and I and then MA, right? If you're familiar with the time series theory, there are three terms: P, Q, R. So P stands for the AR term, Q is for the differencing. So we already have first order differencing, Q equal to 1, we already have it. And then we have R, which is the MA term, right? So here the MA term, we'll see whether we actually need the MA term. We'll start with the AR1 and then we'll see if adding the residual makes any difference. So for MA we are using P equal to 1, and if you're going to use the MA, okay, I'm sorry, for AR P equal to 1, for AR1, for AR2 if P equal to 2, and so on. So for AR term it's the P, and for MA terms it's the Q. So here you see we're going to use both P and Q. So here it is MA as well as AR, so both. Okay, so we'll do the estimation. But remember one thing, that we are using the identify. Okay, so that means we are doing the differencing here as well. So it's the ARIMA 111 because P is 1. So we will estimate the AR1 model first. Okay, now remember that we have already done the differencing, so the I term is already 1. In the ARIMA, the I term is the differencing, right? Stands for the differencing. We've already done the first order differencing, right? So it's already 1. So we'll keep that in mind. Okay, so so for AR1 we use the P equal to 1, okay, in the estimate along with the estimate keyword. Okay, alright, so we will run that. Okay, remember this is for the differencing series, differenced series, so it's basically ARIMA 110, okay, not 100. So that's something we need to keep in mind. Alright, you see the terms here, we have mu. So these are the estimates. We have mu, which is the average, and then you have the beta coefficient, which is the 0.305. It's also significant, right? It's less than 0.05, so it's significant. So that's the AR1, and you have all the diagnostic statistics like AIC, SBC, and so on. So these are going to be used while comparing the time series models, right? So the one with the least AIC and SBC should be the one to be selected finally, right? And then we will see the autocorrelation of residuals. Okay, so the idea is to see ensure that the residuals are not autocorrelated. There is no correlation, but clearly there is some correlation, right? The p-value is significant, so the residuals are correlated, indeed correlated. Let's look at the normal residual plot, and you see that it's not normal, right? So there are two things, two signal that tells us that this model doesn't fit the data quite well. Firstly,
The residuals are correlated, and the plot doesn't seem to be a normal plot, okay, or it doesn't seem to be a normal distribution. The residual doesn't fit a normal distribution. Hence, we will see other models, right? We'll add the MA terms, which is the error term, to the model and see if it makes the model better or the forecast better. Okay, so for MA we use the keyword Q equal to 1. So we'll start with MA1. Okay, okay, let's run this one. Of course, you can use P equal to 2, Q equal to 2, P equal to 1, Q equal to 2, P equal to 2, Q equal to 1, and so on. So we can try all sorts of combination and see which one is the best model for this data. Okay, we'll see the autocorrelation. There's still some autocorrelation between the residuals, so the same problem exists, but the residual plot is much better, right? It's more normal now. So this model is better than the previous one. The ARIMA 111 is better than ARIMA 110, right? So this is clear. Okay, we can try with other models. Okay, there's no issue with that. So we can try, let's say, P equal to 2 and Q equal to 1, and let's see if that's better. It's not better, in fact it's worse. Okay, so this one is the best one, right? The ARIMA 111. Now you might wonder why we have 3 ones. Well, we have P equal to 1, which is the AR term, then this is the differencing term, the first order differencing, and this is the MA term. So we have ARIMA 111 is the final model for us, right? Because among the 3 models that we've seen, the ARIMA 111 gives better results. Like looking at the diagnostics, statistics, we could know that this is better. You also can compare the AIC and BIC, okay, and see the one that's with the least AIC BIC should be the one we should choose. Okay, so that's about estimating, right? And the final thing is forecasting. Now that we are sure that we're going to go with ARIMA 111, we'll use that for forecasting the next 12 months values, right? Syntax is very simple. We'll use the same code, Proc ARIMA. We'll simply add the last part to it, which is forecast, the keyword forecast, and then if we want for next 12 months, the lead is 12. If we want it for next 24 months, we want, we just use 24, or 18 months 18, and so on. Interval should be month because it's a monthly forecast. ID, which is the unique ID, which is date, and we will save it in a new dataset called results. Okay, you can give any name. Okay, no problem with that. And then we'll use the same estimate. Okay, P1 and Q1. Okay, and this is the differencing. Okay, so don't forget this differencing part. Identify var equal to AR. So because the I the order for I comes from there. Okay, so it's a ARIMA 111 model, and let's use this to forecast the future values. Okay, we'll run this, and what we're going to get is the values, the forecast values, predicted values for next 12 months using ARIMA 111. Okay, and you can see the values. So these are the values. So we had 144 observation, now we have 156. That means we've got 12 additional observations, which basically are the future values. Okay, so these are the values, and you see the plot here, and also the 95% confidence limits. So this is how the forecast looks like, and then we have the 95% confidence limit. That means in which range the forecast will lie. Okay, so that's the way you build an ARIMA model using SAS. Thank you.
In this video, I'll discuss about how to perform exploratory factor analysis in SAS. The confirmatory factor analysis will be covered in a separate session. What are the things that I am going to cover in this session? First, I'll do a correlation check of the variables. I'll also talk about how to use a Proc factor for doing factor analysis, and then also I'll also cover the options available with Proc factor in doing factor analysis. Make sure you have gone through my video on factor analysis theory. The name of the video is factor analysis, wherein I have covered the theory on factor analysis before going to this video. To illustrate this particular topic, I'm going to use a data set. Let me show you the data set. The data set has information the on the school students. It's about the performance of the students in class. What are the variables available to us? We have mother education, father's education, family income, score in English, mathematics, science, social science, natural science, and vocabulary. Okay. After factor analysis, I am going to build a model based on based on the performance of the student. I am going to categorize student into good and bad. Okay. With some criteria, I have categorized with student type 0 and 1. 1 is good and 0 is bad. But student type variable, which is a binary variable, is not going to be used for factor analysis. Okay, so that is going to be used in the future regression model. That's the reason why I have this variable in my data set, but this variable is not going to be used for factor analysis. Okay, what is our objective? Well, the objective is that when we will do a regression model, I'm going to do a logistic regression model. Once the factor analysis, I have the factors in place, I'll regress student types with all the other variables, right? So that's my regression equation is going to be. How many independent variables I have? From mother education to vocabulary, I have 8 independent variables, and student type is my dependent variable. Okay. Now we have 8 independent variable, and there seems to be some kind of a redundancy in the data. So instead of using 8 independent variable, we can get down to a very few number of factors. The objective of this session is to how to reduce a number of variables. We have 8 variables here to a very few number of factors, and then use these factors for the regression model. Got it? First thing we will do is to see the correlation. We will do the correlation check first. I'm using all the variable except student underscore type. As I said, that particular variable is not going to be used for factor analysis. let us go to, okay, you can see that there is high correlation among variables, high correlation between vocabulary skills and English. Makes sense. High correlation between vocabulary ability and then social science. Hence, we can conclude that there is some level of redundancy in our data. And when we have redundancy in the data, we need to use factor analysis to come up with a few number of factors out of this large number of variable. We don't have a large number of variable, but we can of course reduce the number of variables from 8 to a very few number of factors. Proc factor is the SAS proc that is used for factor analysis. Proc factor data, name of the data, and then in var you mention all the variables that you want to use in factor analysis. This is the simple form of proc factor syntax. There are options available. We will use the options later. Let us run the simple, the very simple version of proc factor. You will have so many things in the output. Not everything will be covered in this session. The important things will only be covered. You can see a message that 2 factors will be retained. So proc factor says that out of these 8 variables, you can make these 8 variables into 2 factors. Okay, we can group the 8 variables in such a way that we will only have 2 factors in place. We never asked SAS to group them into 2 factors. It's SAS by certain criteria. Well, the criteria is Bayesian criteria. You can read the SAS manual to get to know more about this criteria. Using that criteria, SAS tells us that 2 factors will be retained. Okay. Let's go to the box factor pattern. You can see there is factor 1 and factor 2. Automatically we have 2 factors in place, directly given from the algorithm. Now how do we know that? If you remember my session on factor analysis, what I told is that each and every variable is a linear combination of the factors. Okay, let's take this variable mother's education. So mother's education is a linear combination of factor 1 and factor 2. The coefficient, okay, this is the estimated coefficient. The estimated coefficient for factor 1 is 0.41 and that with factor 2 is 0.69. Similarly, for father education, the estimate, the coefficient of factor 1 is 0.5 and the estimated coefficient for factor 2 is 0.69. Okay, we can write it down like this: mother's education equal to 0.41 factor 1 plus 0.6 factor 2. Similarly, we can write such equation, this type of equations for all the variables that we have used. Now remember one thing. If you remember what I talked, what I taught in the factor analysis video, the theory part I'm talking about. Out of the two coefficients, look at the one which is having a higher value. Okay, usually one of the coefficient will be significantly higher than the other. This coefficient for factor 2 is significantly higher than coefficient for factor 1, right? So 0.6 is greater than 0.4. Okay, hence mother education is explained more by factor 2 and less by factor 1. Got it? Hence mother factor 2 is contributing more towards explaining mother's variation in mother's education. So factor 2 is the latent factor associated with mother education. Now let us go back to the result and see where factor 1 is contributing more. If you see English, the coefficient for English score is 0.77 for factor 1 and minus 0.23 for factor 2. Hence, factor 1 is contributing more to the English score than factor 2. Similarly, mathematics. Factor 1 is 0.77 and factor 2 is 0.17. The coefficient for factor 1 is significantly higher than coefficient for factor 2. Hence, factor 1 is contributing more to the mathematics score. Okay. So there is a trick here, how to club variables, right? We have got factor 1 and factor 2. So how to club variables into separate factor? Okay. Wherever you have higher coefficient, just mark it. First variable mother education, I'll mark this one. Second variable father education, factor 2 coefficient is higher, again I'll mark the second one. And then family income 0.6 against 0.4 for factor 1. So coefficient for factor 2 is higher. Hence, and no other cases, right? In no other cases you have factor 2 having higher coefficient. So only first three variables are the ones where the coefficient for factor 2 is higher than coefficient for factor 1. Hence, the first three variables, mother education, father education and family income, can be clubbed together. Okay, so that come under the factor 2. Okay, in the last 5 variables, in all the cases, the coefficient for factor 1, you can see it, is higher than the coefficient for factor 2. Hence, we can club these 5 variables into factor 1. Okay, so that's how we group the variables. Factor analysis is all about grouping variables into one single factor, right? Okay. Remember, this is exploratory factor analysis, so we have no clue, no hypothesis to start with. We do not have any knowledge or very little knowledge about how the variables actually behave, or if there is any pattern, if at all there is any pattern among the variables that we have used. Okay, the SAS algorithms suggest us that we should be taking only 2 factors, but we have the option of selecting the number of factors. How do we do that? We can use the n factor criteria. Okay, so when we use the n factor option, we can mention there how many factors do we want to be there in the result. Okay, if we want to enforce it, If you don't want to enforce it, we just want to explore it, we can just let the algorithm find it out for us. Okay, that's about exploration. I told, right, proc factor is used for data exploration purpose. So we start with no option, then we go on with options, and then keep changing the options to see if there is more pattern coming out from the results. Okay, let me give 3. Let me see what happens if I ask SAS to give me 3 factor instead of just 2. Let me see the factor patterns. You can see in the output there are 3 factors. Remember the way we group the variables. I talked about how to group variables, right? Now, when you have 3 factors, look at the coefficient which is the highest among all the factors, all 3 coefficient of 3 factors. For the first variable, it's factor 2 coefficient. Second variable, again, it's the factor 2. Similarly, in the third variable also, it's the factor 2. Okay, and then I don't see any valuable thing happening by enforcing 3 factor. The reason is because most of the pattern in the data is being explained by factor 1 and factor 2. Factor 3 is useless, because except natural science, where not even natural science, yeah, I don't see even any place there is no variable where the coefficient of factor 3 is the highest among all 3 coefficients, right? Can you see? Yeah, I can't see that is there anywhere. So factor 3 doesn't add much of value to our analysis, right? So we can try it out, like we can keep increasing the number of factors and see what is happening. Okay, that is the way we do the analysis. As I told in the very beginning itself, that we don't go with any hypothesis, any knowledge, we just keep on exploring. So number of factor is 2. We could see that if we have 2 factor, that is enough, that explains our data set. The next thing that we will study is how to plot a scree plot. To plot a scree plot, we use the option scree, SCREE. Let me run this. Well, what is scree plot? Well, it's nothing but it's a plot of the eigenvalues, and then this particular plot is used to find out the number of factors that should be retained. SAS suggests us that we should be using 2 factors, but we are not sure of it. I mean, because it's an algorithm at the end of the day. How do we select the number of factors to be retained? Look at this plot. Look at this plot. It keep decreasing, then it become flat, right? So there is an elbow-like structure. There is an elbow-like structure of this plot. Wherever we see the elbow, after the second eigenvalue, you can see that all the other eigenvalues are lying on more or less on the same line, right? The elbow-like structure is there at the second eigenvalue, and that is the way you select the number of factors to be retained. Okay, so we will return only 2 factors. Now, had it been the case where if this third eigenvalue, right, it would have been somewhere here, and the elbow-like structure would have been there at this eigenvalue, then we would have retained 3 factor instead of 2. But here it's there with the eigenvalue 2, hence we will keep only 2 factors. That is the use of sgplot. The next thing that we will study is about rotation, or factor rotation. Let's go back and see the factor pattern. There are 2 factors in place. Factor pattern gives us the coefficient that is estimated by using the estimation algorithm, and we find out that which variable is related to which factor, right? We group variables based on the factor loadings. We call it actually factor loading. Instead of coefficient, we actually call it factor loading. Rotation is a method using which we can discriminate between the factor loadings better. So what do you mean by that? Well, the factor loading for the variable father's education is 0.5 for factor 1 and 0.6 for factor 2. There is not much of a difference between them. Rotation helps us discriminating the factor loading. That means making it the distance between the factor loading for one factor and the other factor, making it maximum. Okay, so that it can be clearly distinguishable. Okay, what it essentially does inside the algorithm is that it orthogonalizes the dataset, orthogonalizes the factor scores. Okay, what is orthogonalizing? That means it makes sure that there is a 90-degree or the 2 data sets are perpendicular to each other and not very correlated to each other, and ensuring that the factor loadings are entirely different and there is a distance maintained between them. Let us use it, it will be more clear. We use the option rotate equal to, well, there are several types of rotations available based on the fact that whether we want correlation between factor loadings or not factor loading, factor scores or not. Okay, so before rotation, let me tell you how to get factor scores, right? When we combine variables, we need to get factor score, right? Actual number. Okay, because if you study that first and then go to rotation, it will be easier to understand because things are confusing sometimes. We get it by using the out option. I'll save the factor scores along with my input variables in another data set. I am naming it as students1. You can name anything. Let me go to students1. You can see the last 2 columns, factor 1 and factor 2. You have the values for each and every set of observations. So that is nothing but a combination of several variables together to come up with factor scores. Factor 1 and factor 2 are the final variables we have from a whole set of variables. Only these 2 variables will be used for further analysis. Okay, we call them factor scores. Now let's go to the code and we will use rotation on them. Rotate For rotation, I use the option rotate. There are basically two types of rotations available. Okay, one type of rotation, let me write it, is orthogonal. The other one is oblique. If we want our factor scores to be totally uncorrelated, remember the problem from which we started. We started from high correlation data, right? So we don't want high correlation in our factor. We went into factor analysis just because there was a presence of high correlation in my data. So we don't want any correlation among the factor scores. Okay, no correlation between factor scores. That's one of the way of handling it. Sometimes it's very impractical to impose this condition. Having no correlation between two variables is very impractical, very unrealistic. And sometimes in a modeling setup, we want some correlation, some practical correlation between these two factor scores. Okay. In such scenarios, we use oblique rotation. Some correlation exists between the factor scores. So that's another type of rotation known as oblique rotation. I'll discuss only about orthogonal rotations. That's the most popular one. We don't go into the strictness criteria. Most of the times orthogonal rotation is used. For orthogonal rotation, we need to use rotate option. Rotate equal to vary max. If you want to use oblique rotation, just mention pro max. Okay, rotate equal to pro max, PROMAX. If you are using vary max, it's going to rotate in orthogonal fashion. Let me run it. Let me go to the factor patterns. Yes. When you mention the rotation option, you will get two factor patterns. The first one is the unrotated ones and the second one is the rotated one. Okay, this is the first one. The first factor pattern in your output in your result is unrotated one, 0.4, 0.6. Remember these coefficients, the factor loadings, and let's go to the rotated one. Rotation method varimax, from where the rotation output is there. Now look at the factor loadings. In the unrotated output, the difference between the factor loadings for mother education was very little, right? 0.6 and 0.4. Look at here, 0.4 and 0.08. There is a it's clearly seen that factor 2 is the one which is more related to mother's education. Right. Similarly, second variable, father's education, clearly it is seen. There is no confusion at all. There is a distance between the factor loadings, very high distance between the factor loadings for father's education. Similarly, for all the variables you can see. Okay. Again, I'll repeat how to group the variables into factor. Compare the factor loadings and then mark it. The best thing I do is that I take it to Excel and then I mark it in yellow or something. Okay, you just highlight it and you will get to know. And for mother's education, second factor, father education, compare the two loadings. The one which is higher, again you just mark it. First three variables are associated with factor 2. We group them and call them factor 2. The next 5 variables where the factor loading for factor 1 is higher than the factor loading for factor 2, I group them in one particular factor and we call them as factor 1. The next thing we will learn is how do we interpret these factors, because if we use factor 1 and factor 2 in the model, nobody is going to understand what a factor 1 is and what a factor 2 is. So how do we give a name that is understood by the by everyone? Like if we are going to explain this model to somebody else, we need to give a name to factor 1 and factor 2. Well, mother education, father education and family income show or indicate the family status of a child, whether he has come from a good family background or not, whether your parents are educated and having higher income or not. So that's about the family background or family status. So instead of calling factor 1, we can just rename it as family background factor. Family background factor. So that's our new name. That's the new name of our factor 1. And that is easy to understand, right? The next factor is factor 2. It has 5 variables, right? English, mathematics, social science, natural science and vocabulary. Well, we can call it as academic, what do we call it as? Quantitative and verbal ability. We have clubbed them together. Of course, we can make it 2 separate factors. I tried with 3 factors. I was thinking maybe we can have a factor for quantitative scores and then verbal score, but they have been clubbed together in factor 2. So we can call it as verbal and quantitative ability of the student. We can just use the rename statement in the data statement, like data students 1 rename factor 1 is family background, factor 2 is quant and verbal ability. Okay, the further analysis that we will be doing on this on this uh, factors is to model for whether a student is a good student or a bad student. As I have already shown you, the dependent variable is student type, which is a dichotomous one, so we'll be using proc logistic, right? Student type is my dependent variable. Instead of using 8 variables now, I'll be using only the 2 factors. Family background factor and then the quant and verbal ability of the student. It's a simpler model having fewer number of variables and easy to explain to someone. We can of course explore more, make the factor better and more understandable. Okay, we can explore more and more about it to make the model easy to understand. That's how we perform factor analysis. To summarize, We start with correlation. We check for correlation first, and then if we find high correlation, we go in for factor analysis. In factor analysis, we use so many variables and then come up with a few number of factors. We can save the factor score in a different data set and use the factor score for further analysis. We use rotation to make sure that the factor loadings are very clear and it's easy for us to segregate between two different factors, which variable is related to which factor. And then we use sgplot to know the number of factors that is to be retained. The factor scores are finally used in the regression modeling or whatever kind of analysis that we are going to do with this data set. That's how we perform regression factor analysis. Thank you. Well, to start with, let me just remind you that principal component analysis is very similar to factor analysis. Is used for variable reductions. If we have too many variables in our data set while modeling, that's going to be making a lot of issues. So we need to get rid of the redundant variable. How do you know variables are redundant? If variables are highly correlated, we call them redundant variable. For this exercise, I'll take a data set. It's on student performance in school. I have taken the same data set for exploratory factor analysis. If you have gone through that video, you must be very familiar with this data set. I'll talk about this data set in brief. I have got information on the performance of students or school going kids on a variety of things. Mother's education, father's education, family income, then marks in English, marks in mathematics, social science, natural science, vocabulary. Well, there is another variable named as student underscore type. That variable is a different variable which is not part of the principal component analysis. That particular variable will be used later on for predictive modeling or some kind of a modeling wherein I'll try to know that how can I categorize students based on the information, their marks and their family status. So what are the categories? 1 and 0. So if a student has a value of, the category has a value of 1, it's a good student. If it's 0, then it's an average student. I'm not going to use student underscore type for principal component analysis because this is going to be my dependent variable and I don't worry about dependent variable. Rest all variables are going to be the independent variable, and I feel like there is a redundancy in the data set. Of course, I need to check the correlation before being sure that there is high correlation or there is redundancy in the data. I already have run the Proc correlation. You can run it when you do it. I have run it. Let me show you the correlation matrix. In many places you can see the correlation is well above 0.5. That shows our data has high correlation, something that is not acceptable for modeling, and there is a redundancy in the information. We need to get rid of this redundancy. How do we do that? We can do that by using the principal component analysis. Well, you must be wondering, why are we not using exploratory factor analysis? Well, as I have already mentioned, exploratory factor analysis and principal component analysis are very similar. They are in fact used for similar purposes. One of the main difference between principal component and exploratory factor analysis is that in factor analysis or in EFA in particular, we are more concerned about the latent construct. We group variable and we name the group something. So what happens is that when we build the model, we are concerned about the coefficient of that factor in the predictive model. Okay, in principal component analysis, we don't really care about the grouping much, although we can, we can give a name, but usually assigning a name to a principal component is not something a good practice. And if we use that in the model, we can only predict the dependent variable. Explaining the coefficient of the principal component is not worthwhile. Why? Because the principal component itself is not explainable properly. If it is not clear now, I'll of course go into the detail later on. Okay, let us just start with the the principal component analysis in SAS. Well, SAS has a very interesting feature. You can do principal component analysis using the Proc factor itself. There are two ways. You can do it with Proc factor and Proc princom. We'll go. We'll do it in both ways. Proc factor data. I'll use the data students. That's the main difference between EFA uh, and principal component. The method in principal component should be method equal to prin, PRIN. If you remember in EFA, we either left it without, we didn't mention what method is to be used, or you need to mention method equal to MLE, maximum likelihood. If you don't mention anything, then it will of course do the maximum likelihood estimation. But if you're doing principal component analysis, you need to mention this method equal to PRIN or principal, whatever. You can use PRIN or principal. What else I want? I want a sgplot. That's all I want. And then I'll give variables. I'll give the input variables. So these are the input variables in my data set. Run. Let us run this. Look at the syntax. It's pretty much same as the exploratory factor analysis syntax. Difference is that method has to be print, and we also have used scree. Scree is a plot that is used to know how many components to be retained based on the eigenvalues plot. Let us see the result. It says two factors will be retained by the Minizen criteria. The interesting thing is that although it's principal component, it still says that factor. So there is a there is a bit of a difference. There is a confusion in the terms used here. But never be confused. If you have used the principal option, always read it components, not factors. Although it is all written that two factors, but it's actually component. What is the Minizen criteria? It says that if the eigenvalue is greater than 1, then only it is written. So in how many cases your eigenvalue is greater than 1? Only the first component and the second component. In the rest of the components, your eigenvalue is less than 1. What is a eigenvalue? Well, eigenvalue is nothing but the variance of the principal component, and the criteria is that the eigenvalue should be greater than 1. Only the first two is greater than 1. Hence we will be retaining only two principal component. So out of the 8 variables, we have 8 variables in place. Out of the 8 variables, we'll come up with two principal component. So that's variable reduction, right? 8 variables become two principal components. The principal components are also variables, right? They are also some kind of variable. So that's the way we do the variable reduction using principal component. There is another way of finding it out, that how many principal component to be retained. That is the sgplot. It plots the eigenvalue with respect to the numbers. You can see the variance explained by the first one, it's very high, way above 1. Variance explained by the second principal component, around 1.7. But the other principal component, the variance explained by the other principal components, is well below 1. So these principal components can be ignored. Well, I have been using this word principal component very often. So what does this mean? Well, a principal component is nothing but a combination of a set of variables. Okay, making sure that the principal component is able to explain maximum variance among the variables. We have used 8 variables. So each principal component is a linear combination, or is a weighted combination of the 8 input variables. Look at the factor pattern. Again, the word factor is used. You just need to read it as component pattern. There are two component, component 1 and component 2. If you have gone through the video on exploratory factor analysis, you can use the same methodology to find out the grouping of variable. Okay, but if you haven't, let me teach you again. You compare the loading, okay, the component loading for the both the components. For mother's education, the component loading for the component 1 is 0.41, and for that of component 2 it's 0.69. 0.69 is significantly higher than 0.41. Hence, mother education is related to component 2. Similarly, father's education is also related to component 2, and family income is related to component 2. In all other variables, you see the loading for component 1 is higher than the component 2. Hence, the first 3 variables can be grouped together. So that's like the component 2, and the rest of the variable, okay, are component 1. You can see, right? For English it's 0.77, whereas it's 0.23 for component 2. So component 1 is the one related to English score. Similarly, all the other variables down below. So English, mathematics, social science, natural science and vocabulary scores are all related among themselves, and they belong to the component 1. Whereas family income, father's education and mother's education are related to component 2. The best thing is to do is to copy all these values, take it to Excel. Wherever you see the component value higher, just color it, okay, in the same color, and then change the color if the component is changing. Like here it's changing, right? So change it to a different one. You'll get to know that which all variables are similar and can be grouped together. Here the first 3 variables are similar and hence are grouped together, and the rest of the variables are again similar and can be grouped into component 1. The variance explained by both the factors. The factor 1 explains maximum variance in the dataset, whereas factor 2 or component 2 actually explains much less than that. We have the final communality estimates. Final communality estimates are nothing but the square of the variance explained for each of the input variable. You can see Mother education, 64% of the variance is being explained by the two principal components. Similarly, for father education, 74% of the variance is being explained by the two principal component. Similarly, for English, mathematics, and so on, we that's the way we interpret the final communality estimates in the principal component output. Well, we are interested in the principal component score, and we haven't got that yet. How do we get that? Now it is clear that we have only two principal components that explain most of the things. We don't need to go to the third one and fourth one because they're not very significant one, as we have seen. So we mention this criteria 2 and then out equal to, I'll use another data set to store the principal components along with the input variables. Make sure whenever you are using out statement to save your principal component values, you need to have this n equal to whatever number of principal component you want to save in your data set. In our case it's 2. I'm putting it as 2, much like your n factor criteria and exploratory factor analysis. Okay, you can see to the very right of all the variables you have factor 1 and factor 2. You can rename as principal component 1 and principal component 2. What are these principal components? They are the linear combination of all the other variables used in the input as the input data set. And what are the weights used here? Well, the weights are nothing but, you can see, right, weights are nothing but the factor loadings. So if you, what you can do is that take this value, okay, factor 1, and for the first observation take each weight. So what is the weight for mother's education? 0.10, right? So 0.10 into 3 plus 0.13 father's education into 4 plus 0.11 family income into into 2 and so on. So it's a linear combination. It's a sum product of your factor loadings and the corresponding values of your input data sets. That's how we compute the principal component. Instead of, so once we have the principal components in place, we need not have to use the variables. Instead we can use the principal components directly in the model building exercises, and that's how we reduce the number of variables from 8 variables to only 2 components or 2 artificial variables. Remember, in the exploratory data analysis we used to assign a name to factor 1 and factor 2. It's difficult really to assign a name in a principal component because they are very much mechanical in nature, and it may not be suitable to have a name for them. Okay, another way of doing principal component analysis is using Proc comp data students where input variables and then run. Remember one thing here, that yeah, so one thing I have forgotten to mention. What about the rotation? We use rotation in factor analysis, right? So what is a rotation? Rotation is nothing but it's some kind of a orthogonalization of the data wherein there is a clear distinction between the loadings, right? So you can clearly distinguish which particular loading belong to which principal component. There are two types of rotation available, the orthogonal and oblique. In orthogonal rotation, your principal components are perpendicular to each other, whereas in oblique rotation, principal components can be correlated in some way. Okay, there may be some correlation, but in orthogonal rotation, there won't be any correlation between the principal components. That's the strict criteria, because we started with the high correlation in your data, so we don't want any more high correlation in the reduced variables or in the artificial variables or in the principal components. Rotation is equal to vary max rotate is equal to vary max. Was there any error? Okay. Well, when you use rotation, you will have the unrotated result followed by the rotated result. We have seen the unrotated result, that is what was there before, and then when you use the varimax, you will have the rotated result in front of you. Now you can see your factor loadings are much better, in the sense that you can clearly distinguish between factor 1 and factor 2 variables. You see the difference between the factor 1 loading and factor 2 loading for mother education, 0.08 and 0.79, huge difference, right? So it clearly says that mother education belong to factor 2 or principal component 2. Similarly, father education belong to factor 2 or principal component 2. There is a clear distinction. There is a, the distance between the loadings is very high, right? So that's where the rotation play a very significant role. Okay. Also make sure that the factors or the principal components are not at all correlated. You can check it out also. There are two variables we have seen, right? Take the correlation between them and you will see that it's close to 0. Okay. We can also use proc print com data and then student name, and give all the input variables that we have used, and we can just run and get a similar result. You must be wondering, why do we have two procs for doing the same thing? Well, I also wonder the same thing when I learned for the first time. Um, so far my knowledge goes, the two methods are there, because both the methods have got flexibilities. Proc factor is more flexible. You have rotation possible here, you have script plots, you have so many options available to you. Proc printcom is something that by default assumes that your principal components are uncorrelated. You cannot have a correlated principal components. Well, the one of the important thing which is looked at in principal component is that the principal component should be in principle uncorrelated. Okay, but sometimes during the research we may need the principal components to be correlated to some extent. Proc printcom cannot handle it, but proc factor can actually handle it, because we have the rotate option here. Okay, and there is a slight difference in terms of their estimation. Okay, so what is the difference? Well, in proc factor, the estimation happen in such a way that in such a way that the total variance, it maximize this total variance. Okay, and these variables are actually standardized, the input variables. Hence the total variance is nothing but when the variable is standardized, it means that it has a variance of 1 and mean of 0. Okay, how do we standardize? Well, you can watch a video on standardization of data. Um, I have I'll put that video. Just to tell you in brief, standardization of data is nothing but you subtract the mean and divide it by the standard deviation to standardize it. So in a standardized data, your mean is 0 and your variance is 1. Okay, as well as the standard deviation. Your mean is 0 and variance is 1. That is the standardized data. In proc factor, it uses the standardized data and the total variance is nothing but sum of all the variance. Each variable has a variance of 1 because it's a standardized data. So what is the total variance? It's the sum of 8 ones. So total is 8. Whereas principal component maximizes the variance of the eigenvalues. The variance of the principal components rather. Okay, so so variance of the principal component is nothing but eigenvalues. So it makes sure that some of the eigenvalues is maximized. Okay, so that's the main difference. That's theoretical though. We don't need to bother much about it. If you are a if you are somebody who need to understand the application part of it, not the the background theory. But we can always get back to the same result. Okay, let us run it first and we'll see what is the difference in the result. Okay, let's go straight away to the eigenvector. Yeah, you can see that in proc factor we used to get only two principal components. Rest all principal components are there, but they are not shown in the result because they are not very significant one. As we have seen, the algorithm recommends only two principal components. On the other hand, we do not have the luxury of having the recommendation from the algorithm when we use the proc princom. It gives all the principal component. How many number of principal component we can have? We can have as many number of principal component as the number of variables. We have 8 variables, so we can have 8 principal components. If you see, the first two principal components are actually good enough. Rest all do not have a good factor loading. Or is that wrong? Well, yes, that is the thing. First look at the eigenvalue matrix. The first eigenvalue is 3.88 and the second one is 1.64, but all the other eigenvalues are less than 1. So the best thing is to select the first two principal component. So we will select only the first two principal component and based on that we'll group the variables. Okay, so that is the way we do the principal component using princom. Okay, the groupings will be same because if you see mother education, father education and family income, in all the cases the loadings are higher than the first principal component 1, right? Hence principal component 2 is a combination of first three variables. Similarly, principal component 1 is a combination of rest of the variables: English, mathematics, social science, natural science and vocabulary. Okay, so the results are same, but the values are different. The factor loadings are different. And that is the reason. What is the reason? I mentioned that previously. The estimation method is different. Proc factor uses total variance, maximizes total variance, and proc princom maximizes the variance of the orthogonal principal components. And that's the reason why there is a difference in the loadings. But of course we don't really bother about the loadings much We bother only about the grouping of the variables, right? Now, one thing that I'll show you, that how do we ensure that the results are consistent from both the procs. Well, just to show you an illustration that you don't need to understand this, just to show you an illustration that they are essentially same. Sometimes we may have a confusion, and we do not need to be very confused. I'll show you that proc factor result and proc principal component results are exactly same, even in terms of the loadings. Remember one thing, principal component value for mother education is 0.20, and for print come to it's 0.53, and we'll run proc factor and let's see what are the values. Okay, there is a difference in the scaling. Okay, because of the difference in the estimation method, there is a difference in the scaling, hence we have this issue. Now let us let us use this code proc factor data students, and then we're scoring. We are getting output for all the principal components here. We are forcing it to give all the principal components input variables, and then we have used ODS output, where we have got the standardized coefficients in this particular data set, COF, standardized coefficients. Then we standardize the factor score. Okay, we have factor score from factor 1 to factor 8. We standardize these factor scores, and then we print the output data. We have used a standardization factor, the scaling factor, which is 1 by square root of n, where n is the number of variables used. It's confusing, but you don't need to understand this code, because it's not required during in the principal component analysis. I'm doing this illustration just to show you that the results are consistent. Let me run this code. You can learn this, of course, when you have fairly good command over the principal component analysis. Okay, let me show you. Yeah, this result is from the proc factor, and look at the loading on factor 2, it's 0.20. Remember what was the loading from the print comp? It was 0.20, right? But earlier when we ran proc factor here, the loadings were different. With what we did here is that we just standardized the factor scores or the principal component scores. That is the only difference. We just need to standardize it in some way, so that there is consistency. But we don't need to do it, because factor loadings are not very important for us. What is very important for us is the principal component values and the groupings. Okay, and these things are not they don't get affected because of the change in the factor loadings. Hence, the conclusion is that you can, instead of using 8 variables, you can use the 2 principal component score that you have saved in your data set. Here in the student 1 data set, you have saved your principal component. If I want to categorize student into good and bad, I can take my dependent variable student underscore type. Let us go to the okay, so I can use student underscore type as my dependent variable, and then as my independent variable I can use component 1 and component 2. I don't need to use any of these variables. Okay, that's how we reduce the number of variables. To summarize, principal component is very similar to exploratory factor analysis. There is a great amount of chances that you might confuse both these techniques. Remember, They are essentially the same in terms of their uses, but the underlying assumptions are different. So you need to be a bit careful. There are two procs available in SAS: proc factor, proc per income. You can use. When you run both the procs, you will see different factor loadings or principal component loadings, but the groupings don't get affected. So you need not worry. You can use one of them and save your component score in your output data and use that in the model. Okay, so that's about principal component analysis in.
Hi, in this video, I'll show you how to perform survival analysis in SAS. Make sure that you have gone through my video on survival analysis theory in this channel before going through this video. I have covered the theoretical part of survival analysis in that video. It is always good to know the theory before knowing the application, hence go through that video first. In this video we will study three things: how to use proc life test in SAS to do the Kaplan-Meier estimation. Just to remind you, Kaplan-Meier estimation is one estimation method that is used to estimate the survival function. Then we will learn how to interpret the product limit table, which comes as part of the result in the estimation process. And then finally we will learn how to interpret the survival curve. For this illustration, I have taken a medical data set. There are 500 patients who have gone through medication, and the medical authority wants to know that how many of them are surviving beyond a certain period. Okay, look at the data set that you can see on the screen. ID is the customer ID, or sorry, the patient ID. I have got 1 to 500, so there are 500 patients in total. Length of follow means till what time they were in the study, the patient was in the study. Then f stat is the status of the patient. 0 is surviving, 1 is the person died. So the event of interest is dying or death. As you know, survival analysis is a kind of modeling where we model the time to event. So if you look at the patient 4, the status is 1. That means the patient has died at what time? At 297th day from the date of medication. Okay, so what is the sensor variable in this case? The sensor variable is the f-stat. You will see so many cases where the patient is surviving and or the patient has dropped out from the study. Okay, and these cases are censored cases. So the f-stat variable indicates whether a patient is having the event, which is death, or it's not having the event, it's surviving till the end, or it's dropping out from the study in the f-stat is the variable that shows whether patient is dying or it's surviving or it's dropping out. Okay, let's close the data set. It is always good to do the frequency table to know the distribution of the events and non-events.
and the minimum maximum of the time period, the length of the time period that is followed. So I assume that you do it before doing the analysis. You have to use the proc means proc frequency to do the exploratory data analysis before doing the modeling work. I'll straight away go to the modeling. Proc live test data medical. I'm going to write here at risk. So this is an option which gives you how many people or how many patients are at risk at different time point, and then I'll plot the survival function. Then time, length follow, f start 0. Let us understand the syntax. Proc live test is the proc that is used for estimating the Kaplan-Meier function. At risk is something that is used to know what is the count of patient at risk at different time points, and then we use the plots for plotting the survival function. In time, we need to mention that what is the time period of following the particular event, length follow or LENFOL. That particular variable is our time or the duration for which the patient is under study. And then f start is nothing but the censored variable, and what is the value that shows censoring? Well, it's 0. If it is 1, then the event has happened. What is the event in this case? It's death. If f start is 1, then the patient has died within the study period. If the status is 0, it hasn't died, or it's a censor case. We have no clue what is happening with that patient after the study period. And then run. Let us run this. You can see on the screen the product limit survival estimate. Let us understand this first. Number of people at risk, number of patients at risk, 500. In the 0th time, everyone is at risk. Nobody has died. Okay. Then in the first day, on the first day, one person died, and then second person died, and gradually 8% in total died on the first day. Not 8, it's yeah, it's 8% died. So on the second day, before the second day, 8 people have died in the first day itself. So total number of people who are at risk in the second day is 492 now. The survival probability is 1 in time 0. That means the probability that individual will survive beyond time 0 is 1. Everybody is going to survive. But after time 1, when 8 people have died, the survival probability decreases, obviously, because people are dying now, and then the probability of surviving beyond time 1 reduced, and it is reduced to 0.98. And then there is a corresponding failure also. Failure means your death. Survive, it's the complementary. It's just 1 minus 0.984 is your 0.016. So your failure rate is like 1 minus your success rate or your survival rate. Okay. In the time period 2, again 8 people are dying. So for the time period 3, your survival probability decreases to 0.96, and so on. It will go on decreasing, and then the number of people at risk is going to go down with time, and there will be a point. This will go on till the number of time points we have. We are
having in total 2358 time points. um, till that time point we will be observing what is happening to these patients and how many people are at risk and what is the survival probability and so on. The survival probability, as you know, it's unconditional probability. That means it's not conditioned on the fact that how many people have died previous to that, so it's completely independent of that. um, all you know that what is the probability of survival beyond a particular time t, that t will varies from 1 to your end of the period. If you have more than 2000, so from 1 to 2300 time point. When you plot this survival probability at each point, each time point, you get a survival curve. You can see on the screen. In the x-axis is the survival distribution function, which takes value from 0 to 1. It's nothing but the probability. At time 0, everybody is surviving, so the probability of survival is 100% or is 1. Okay, but at time goes, the survival value or the probability goes down gradually, and by the time it's the 500th day of the study, you can see 25% of the population have already died, only 75% are remaining. Or in other words, how do we interpret this? Well, beyond the 500th beyond 500th day, the probability that a patient is going to survive is 0.75. Similarly, at 1000th day, you can see on my marker 1000th day, the probability is somewhere around 0.65. So the probability that a patient is going to survive beyond 1000th day is 0.65. Similarly, it's 0.5 on the 2000th day. Okay, that's how we interpret the uh, survival curve. Why is it so interesting to us? Because we get to know that how the events is happening, at what rate it is happening. We can compare different survival curves across different different categories. For example, we can do it for male and then do it for female and then compare. How do we compare? We compare in such a way that what is the mortality rate and how do we see a difference between male and female population. So these are the cases where we use the survival function. And one of the peculiarity of the survival model, you might have already have this question in mind, that what is a dependent variable, what is a independent variable. Usually we always want a dependent and independent variable in the model, but we don't have it here. So what is the reason, and what kind of a model is this? Well, this is kind of an univariate analysis where we just need one variable for us. We just need in fact the only thing that we need is the status of the patient and the length of the time followed. So there are two variables, and then we just plot it by taking the unconditional probability. That is all we are doing it here, and Kaplan-Meier estimation is the one that we are using it here. Very simple but very powerful analysis. The same thing can be replicated in other fields also. We are analyzing death here. We can analyze anything, any event in the credit risk industry. We can analyze default, we can analyze delinquency, we can analyze bankruptcy, payoff, liquidation, so many things. Similarly, in the marketing industry, we can analyze when is the customer purchasing. So purchase is the event. When is the customer leaving the company, or being loyal to company. So these events can also be plotted as a survival curve, and we'll get to know at a portfolio level that what is the percentage of customers who are surviving beyond a particular time point. Okay, so that gives a fairly good idea about how the the business events happens across the time period. and it really is helpful taking in very important decisions. That's pretty much about the Kaplan-Meier estimation. We can of course go on to the more complex estimation method, and then a couple of things we can do. We can compare survival analysis plots across different categories and check it out. That we will see in a separate session. For this session, that is all we will learn. Thank you.
In this video, I'm going to do an optimal pricing problem. So I'll make use of the optimization techniques that we have learned in the previous video, and then we will find out what is the optimal pricing. So the problem is like this. Suppose a company has two competing products. So the company produces two different products, and a customer has two choices: buy product one and buy product two. Same product of different types. Um, so there is a choice, and we assume that the choices are mutually exclusive. Now, how do the companies set the prices of the product so that its profit is maximized? So there is a competition between two different products from the same company. So the competition is internal in nature, it's not external. So the competition can be controlled with a selection of suitable price. Now the company has to set suitable price in order to maximize the profit. So this is a profit maximization problem. Now in this case we are going to use some marketing some pricing literature. So the pricing literature says that the volume that should be produced when you have a competing product should be given by exposure. Exposure is just a constant into exponential of minus of alpha into price. So alpha is just a parameter. It's a parameter of price volume model divided by exponential of minus of alpha into price plus exponential of minus of beta into q. So q and p both are price. So p is the price of say product 1 and q is the price of product 2. So the volume that one should produce for the volume that one should produce for product 1 is given by this particular product volume formula. Similarly, when we change to product 2, we will just take the beta into here. Okay, so let me write the formula for product 2. Okay, so this is volume should be produced for product 1, volume should be product 2. So I'll just change it to beta, and this is how my equation is going to be. So this is into q. Okay. Now this formula has come from the literature. So we need to decide what's the value of what's the value of p and q. Now the value of alpha and beta, these values, the parameter values, we already have been given to us. All we need to know is the volume 1 and volume 2, p and q, and the maximum profit. So these 5 things are of interest to us, right? The formula could change actually with with industry, with different products. The formula will change, but the technique will remain same. The one that we are going to use will remain the same. Few more informations. Profit is always given by revenue minus total cost, right? And how do you find revenue? Revenue is price into volume, and total cost is unit cost into the volume. So using this 5 formulae, we are going to write an optimization code in order to find out the optimum price of the two products, right, which maximizes the profit. So that's the condition. So how do we do that? So we are going to write a proc opt model. The proc opt model is the optimization procedure available in SAS. So the first thing to do is to declare the variables of interest and the different given variables. and then we will declare the objective function, and finally we are going to solve it. So let's go step by step. So the first variable I'm declaring here is alpha, which takes a value of 0.05. So that's given. And now this is a number. So we define it as a number. Okay, these are all constant. Sorry, this is not variable, this is a constant. Again, the next constant is the beta, which takes a value of 0.1. Then cost of making an extra product. Okay, for product 1 it is 15, for product 2 it is 20. The fixed cost of making product 1. So there is only a fixed cost and an additional cost for every product, right? So the fixed cost for making product 1 is 100, and the fixed cost for making product 2 is 120, and the exposure constant is 1000 again. So these are all given. These are all given to us. Okay, so these constants are given to us, but the variables are unknown to us. Okay, so what are the variables? So now let us declare the variables. Okay, so we have got P and Q, the prices of product 1 and 2. So product 1 price is P and product 2 price is Q. Now the constraint here is that this true has to take a value of greater than 0. Price cannot be negative, right? We cannot have a negative price. Now we and the other constraints, and the constraints are the volumes. The minimum number of products for product 1 should be 130, and the minimum number of products that the product 1 should be produced is the 20. So these are constraints given to us. We cannot have, you know, lesser number of products than this. Okay, above that, what should be the optimal, or what volume should optimize or maximize the profit, right, given these constraints. So there we have got 4 constraints with us, right? Now the profit maximization, as you have seen, is just total volume minus total cost, right? And volume is given by this formula. So we just write an imp var. So imp var keyword, what it does is that when you have a complicated formula, and what we have already seen that the volume formula is very complicated. So if you write in a profit function, it's going to take a lot of space, right, to write. So instead what we do is that we just write the volume before the volume formula and store it in V1 and V2, right? And this V1 and V2 we are going to use it in the final profit maximization formula or the objective function, right? If you, I mean, we can as well use this entire portion over here in the place of V1 and V2, but that's going to make it the formula very clumsy. So for a better look and to make our life simple, we can actually use the imp var function here. Okay, now we have got volume 1 and volume 2, the same formula that we have used. I just explained before writing this code, and then finally we will write the objective function. So objective function is profit, so which is the total revenue and the total cost. So total revenue is price into the volume, so unit price into volume, right? So I don't know what is the the price of the product, what price should be. That's the variable, I need to know about it. And the Q is the, again, that's a variable as well. I know what is my unit costs, right? So unit cost in the volume, so it gives me total cost, and then fixed cost, and then unit cost for product 2 into volume. Hello. Hi. Yeah, hi Srinivasan. Hi, how are you? Yeah. Okay. Right. Right. Okay. Yeah, sure. Over the weekend, we see. I'll be giving you more access to more different study packs, and also in this weekend we will have a session. Okay, one-on-one session. No, first thing is that basics, right? You need to know the basics before knowing. Those things are will be very advanced, right? If you want to know how calculate like simulation, VAR calculation, or credit risk modeling, financial forecasting, you are very so first thing is to have your basics clear, okay, and it takes little time, okay. So let's have the basics, right, right. Yeah, that's what. Like logistic regression is important. So you just focus on linear and logistic. Once you are done with this thing, we'll directly go to the risk analytics. Okay. And before that also, I'm going to give risk the access to one of the risk analytics folder. You can just go through all these more. It's very vast actually. It may take a lot of time. But yeah, you can go through these videos and all. Okay. 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 Hmm. Okay. Hmm. Yeah. So I have got data sets. See, I have got data sets there. I have got data sets. So if you can just do one example, that will be good because that is more important when you actually do it yourself. That will be good. Just do an example and send it to me. I'll just do the correction and send it to you back and with my feedback. Okay. Yeah. Sure. 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 Yeah. Sure. Sure. Makes sense. Yeah. Okay. Thank you. Okay. Bye. And then we will call the solver which is going to solve for us. So we write solve, so we just call the solver for that, so which is going to optimize the objective function. And finally we will print the variables. The variable with us is the prices of the two products, the actual quantity that is to be produced, and the maximized profit. What is the maximum profit that we can expect, right? Now once this is ready, we can just go ahead with the fun. Okay, so let us go to the output. So when you look at the results, first see whether the objective function is maximized or not. And it says the solution set is optimal. If it is not optimal, then that's an issue. So it has to be optimal all the time, right? And then how many iterations it took? So 18 iterations. So it runs very fast. And then another thing to look at is the objective function value, that is 3075. So the maximum profit is 3075.94. Okay, that's our objective function, right? Yeah. And the variables of interest, and we can say the optimum value of this. So the price of the first product should be 37.32. That's the optimal price. The price of the second product should be 33.44. The volume of the first product should be 130 and the volume of the second product should be 29. Remember that for volume we have a constraint that volume 1 has to be minimum 130 and then volume 2 has to be minimum 20 only, right? So volume 1 is 130, so that's only the constraint values, but volume 2 is more than the constraint value, so it is 29.64, or if we round it up it will be 30, right? So and the profit, when we have the optimal variables, the optimal profit will be, or the maximum profit will be 3075.9 units. Okay. So that's the way we find out the optimal price and volumes of different products. Now this is very useful, especially in a case where the products are competing, the competing in nature. For example, um, an FMCG company generally they have multiple products for the same category. For example, in the case of Unilever, you will have different types of soaps and they will be competing with each other. Now the same company but different different products of same type. So they need to come up with an optimal price which maximize the profit, ensuring that none of the product gets affected by the competition, internal competition. That's important, and that's how we can have a better strategy. We can extend this problem to different other problems. It may not be just limited to price. We can also include also have volume in place, and then we can have multiple products, not just two products. We can have three, four, five, any number of products we can have, um, and we can find out the optimal prices of these products. And it need not be similar product. We can even have different products, but the business logic has to be good in the sense that we have this volume and price model, right? We have used here. So we need to look at the literature and find out the relationship between different product prices and the corresponding volume. Once that is clear with us, doesn't matter how many number of products are there, how many number of variables are to be found out. It's pretty easy to implement this algorithm and find out the optimal variables.